Okay, we'll wait for a couple of minutes. I think we're shy of 2:30 or. Oh, more issues. Michael, then it's out of the frying pan and into the fire. Next week is grading, okay? Yeah. I'd rather do this than do grading. All right, welcome back. I guess we have some folks online and whoever is there here. So we'll be having two in-person presentations, first by Steve Ruff and then by Michael Rowe. And that should be mostly done by 4 o'clock. And then we take a slightly longish break then. Between 4 and 5, there might be some students who are interested to go and listen to Binod Srinivashan's Institute Colloquium. And so thanks to both Michael and Steve, they agreed to basically move their talks 30 minutes ahead of the scheduled time. And also to Martin, who has now pushed his talk by about 10 minutes, right, Martin? And that makes it about an hour. And so, but we'll still finish by 6 o'clock. But between 4 and 5, the idea is maybe we can, most of us are going to be here, but we can start collating the stuff that we've discussed. Because the goal is to have some kind of a white paper at the end of this meeting. So we can start scribbling old school style on the blackboard and keep it until tomorrow. Take a picture of that and then not do anything after that. All right. So over to you, Steve.
All right, thanks for coming back after lunch. I'm going to try to have this talk be sort of engaging enough that it will not put you to sleep after a meal. So this is going to be kind of the story of the discovery by the Spirit rover of this important deposit on Mars, and so the details will be forthcoming. So let's start with literally the big picture. The global context. The Spirit rover was sent to this landing site, Gusev Crater, because of the geomorphic features really of there's a huge channel that goes into this hole in the ground, right? So it's 1,000-kilometer long channel thought to have been carved by water. And here's where that channel arrived in this large crater, roughly 140 kilometers or so. So the simple concept was that water ponded from the flow here into here, and there's even evidence of potential eroded delta deposits. So this, again, was back in the early 2000s that the decision to go to this place with the Spirit rover was made based on the idea that we would go to an ancient paleo lake. So here I'm going to zoom in to a Themis visible image. And so the next view is the landing ellipse. And I wanted to show this in part for Shyama, that the landing ellipse of the Spirit, both Spirit and Opportunity, was large, roughly 150 kilometers by 20 kilometers or so. So it was a huge region that was deemed safe enough, and these landing ellipses are the sort of a probability of landing within this place on Mars after cruising from Earth. And in this case, Spirit landed in this really opportune spot, an ideal spot, in part because if you notice, there's this darker toned surface here relative to all of the rest of this lighter toned surface. All of the lighter tone area is very dusty. So the dust cover index that I have kind of shows yellows and red colors. This is a place where dust has been lifted by thousands of dust devils, so these swirling vortices are able to essentially vacuum up or lift dust. And so all of this area is less dusty, although I'll show in a minute that it's still quite a bit of dust. But this was just a fortuitous place in this otherwise huge landing ellipse that Spirit arrived. And I wanted to show sort of the payload of this rover. And I'll start with the instrument that I was most directly involved with, the Miniature Thermal Emission Spectrometer, also known as MINI-TESS. Essentially, it's an FTIR spectrometer down in the belly of the rover, and it uses a periscope. It's actually looking out the other side to collect long-wave infrared emission, bring it down to the spectrometer, and generate a long-wavelength infrared spectrum. There was a multispectral stereo camera up on this mast. There's down on this robotic arm, 6 degree of freedom robotic arm. The non-scientific tool, but incredibly helpful, was this rock abrasion tool, the RAT, that you could grind off this weathered surface of a rock to get a better view with both a microscopic imager, and there's the resolution, and a Nussbauer spectrometer, and also an APXS, which is essentially XRF, so X-ray fluorescence. This uses alpha particles to do that elemental chemistry analysis. And for scale, there I am 22 years ago, on the night or the day. This is at Jet Propulsion Lab, one of the most exciting days of my life when we were expecting the first arrival of Spirit. It was the first of the two to arrive. And so you can get a sense of the scale. By the way, the camera eyes were essentially intentionally at the eye level of a human to sort of give you that better perspective. And I'll point out here that the wheels, for future reference of other images I'm going to show, are about 1 meter apart. So the tracks are a convenient scale bar, really. Okay, so one of the first things that we discovered, literally before we even drove off the lander, we could use the infrared spectrometer to survey the scene. And this was not the place that some had hoped in terms of landing on lake lacustrine deposits, lake sedimentary deposits. Some people expected or hoped for that. Others, including me, were skeptical that there would be lake deposits, and sure enough, it wasn't. It was basaltic lava, olivine-rich basaltic lava, and subsequently, thanks to crater counting by Greeley et al., basically the surface that you're seeing here that includes there's actually wrinkle ridges, that some of you may be familiar with what those are, and you can see these lobate margins of the lava that flowed in and surrounded some of this pre-existing terrain. So we landed on basaltic lava, not a lake bed. So that was the first sort of discovery and really disappointment of this mission, is we didn't land in a place that was astrobiologically interesting because it was resurfaced over time. Nearby, and again, it was fortuitous, we could have landed kind of anywhere here. We landed right next to this previously unnamed feature called the Columbia Hills, and it's surrounding, or the lava flows surround the Columbia Hills. So even from the orbital information, we could recognize that we could conceivably go to this place that was older than the lava flows that we had arrived on, with the hope that we would actually find older. Maybe that's where we could find remnants of ancient Lake Gusev. Now I'm going to show you the ground view this is literally while we were still on the lander. And if you don't know, these two rovers landed with airbags, not retro rockets. So they used airbags in a cocoon about higher than this room to bounce across the surface, deflate. And now it's kind of interesting. You can see it used to be white material, and then as that white fabric dragged across this dusty surface, it picked up the red dust. These don't look like sedimentary lake deposits, right? These are basaltic lava, chunks of rock. And the Columbia Hills were named in honor of the Columbia astronauts on the Columbia shuttle, which included the first Indian-born astronaut, Kalpana Chawla, from northern India. Well, unfortunately, this mission launched in January 2003 and came back to Earth in pieces. So all 7 astronauts were killed 2 weeks after they launched. This was literally during the time, the final assembly of Spirit and Opportunity, and they were given on their high gain antenna, the X-band antenna on the back is this memorial to these astronauts. And to further sort of memorialize them, we used these 7 hills of the Columbia. Now Columbia Hills are named after each of those astronauts. So here's a view from the high-rise camera much higher orbital or high resolution orbital images. And I wanted to just point out that again, you can see this sort of embayment relationship of lava surrounding this pre-existing terrain, which means the Columbia Hills and the terrain within are older than the 3.65 billion year old. The spec that we gave them, 90 Martian sols. None of them imagined, nor any of the scientists, year after year after year, these rovers kept going. Why? Because the solar panels kept getting cleaned off by dust devils. So, you know, it's almost something that can, well, depending on, so InSight didn't have, InSight didn't have this benefit because, and you can tell from the high-rise images, there are no dust devil tracks around InSight. So InSight died because of dust accumulation. Okay, so here we are. Are we back? Okay, that's my phone. Yeah. Okay, so we did this. Okay, so this view, I already talked about that. Now I'm going to zoom in. This is going to be sort of an oblique view with high-rise DEM. Now, Husband Hill, Rick Husband was the commander of the shuttle, and so that's why you're seeing this Husband Hill. Home plate was our last best hope for evidence of ancient Lake Gusev. So from the orbital images, you know, we could tell that there was something novel about this light-toned terrain here. And does home plate translate in Indian culture? It's a baseball reference. Okay, all right. So why? Because it looks a bit like a baseball plate. So that's as sophisticated as that naming was. So we left the basalt dungeon, as some on the team were describing it as the basalt dungeon crossing over this plain. We started to see very different rock literally as we transition. You can see this margin of the lava flows eroded and then up into the hills, up and over. The whole time hopeful that there might be some evidence of ancient Lake Gusev. Didn't find it. But we, you know, had sort of an ultimate target of this home plate feature as this last best hope for ancient Lake Gusev terrain. And here now in full resolution, and it's fun that you can see that's the Spirit rover down there. And you can even see the tracks, the 1 meter apart tracks at this resolution. So home plate was this feature. You can see, you know, it has some interesting sort of morphologic details. We approached it from the north, and you can actually just make out the tracks. We literally drove up here, and what we found was encouraging, exciting in terms of, wow, this is the first beautifully layered terrain that we could see. And you're seeing this sort of panoramic view, fisheye sort of style, so it's distorted. But look at the layers. So there was a lot of excitement that maybe this really is the sedimentary rock that we're interested in. Well, it turns out that we happened to drive up to a place with a view that I'm about to zoom in on here. And so scale bars over here on the left. So look at these layers here and look at this little distortion right here. There was enough volcanologic experience on the team to recognize the possibility, the likelihood that that's a bomb sag. So explosive volcanic eruptions can throw out rocks. This is a much larger rock here in Iceland from my colleague Jim Rice. There's a pen for scale, but you get the sense of this. Not only is there ash deposits, pyroclastic deposits, but they're even moist enough that they can soft sediment deform. And so that's what we're seeing here. And so this was a clear indication of some kind of phreatomagmatic explosive activity that produced home plate, not a lake. So this was clear evidence of volcanic activity, not a lake deposit. So there was both disappointment and excitement to see something like this. So next up, I'm going to now take you to the place that did become very exciting. So if you've heard anything about home plate silica, it's a bit of a misnomer because it has nothing to do with the top of home plate or even the edge. It's over off to the side in a place that we named cleverly the East Valley. So not very provocative. So this is a great view from the front HAZ cam. So the HAZ cams are, as the name suggests, they're hazard avoidance cameras mounted down low. You started getting this distorted look. And remember that the wheels are roughly 1 meter apart. This is the discovery outcrop of this story. So this whole story is just this fairly unimpressive, knobby little outcrop. The PanCam color image that has now become sort of famous is taken right there. And so there it is. Elizabeth Mahan. We were naming, these rover teams, at least the NASA ones, use a naming convention. And in this case, home plate, baseball. We were using baseball names. And in this case, we decided to use, during World War II, when men were off in the war, women were playing professional baseball. So America had a professional women's baseball league. And so we used the names of professional women's baseball players, and Elizabeth Mahan was one of them. So now her name is sort of etched in Mars history in a very weird way. And there's my Swiss Army knife for scale. It's a quick, yeah, right? That's detail. All right, so that was the view, and we actually drove around the side to get a different view for mini tests. So the mini test instrument it's not an imager, it's a single spot, and it's a fairly big spot. So we needed the biggest sort of rock that we could see. And I took so these are about 15 centimeter diameter spots. And I knew that this field of view would be a mix of the rock that I cared about and background that I didn't. So I took a background measurement so I could subtract out the background. There's Elizabeth Mahan right there. And this is where it became very clear what we had discovered. So this is a beautiful infrared spectrum for mini tests on top, background corrected, and a lab version of Opal A, amorphous silica, which is amorphous hydrated silica. So it's like amorphous hydrated quartz, if you want to think about it that way. And so this is about as good as it ever gets in spectroscopy, where you essentially see feature for feature, all of those features lining up. By the way, the CO2 is a reference to atmospheric CO2 in the Mars atmosphere. Did you know it's a greenhouse gas? And it's absorbing infrared right here. And so you just cut that part out and you don't have the benefit of that spectral part, but fortunately there's no features here. And just to drive home, Opal A, some of you may know, it doesn't last for more than 1 million years or so in a natural environment on Earth because it turns into quartz. So that amorphous stuff and goes through this paragenetic sequence and ultimately leads to microquartz or chert in some cases. And you can see how different. There's no confusing this stuff for this stuff. So we know that after billions of years, how long it was actually exposed is a different question. But billions of years ago, Opal A was produced and it stayed that way. It didn't turn into this. So that's important. Okay, next up. So this now becomes part of the story where as we were driving up Husband Hill, the rover was sort of struggling in the loose regolith, and we were exposing light tone material underneath, and the ARM deployed APXS instrument, XRF, was seeing this pronounced enrichment of sulfur. So in this case, it's shown as an oxide, but 32% oxide of sulfur. And we kept then seeing these same kind of occurrences as we drove up and over and down. So these places where there was fairly thick, loose regolith, the rover wheel would churn up that soil, that material, that regolith, and see this light tone stuff underneath. And in all cases, it was sulfur rich. And I will add that in some of the whiter places, it's actually silica rich as well, but it's mostly sulfur rich. The opal and silica story is interesting. We would see it now not spread around like you're seeing the sulfur, but always by itself. None of these occurrences of this opal and silica had any sulfur enrichment. So the sulfur enrichment seems to be only in the regolith, not in the rocks, which is part of the story as well. And here is the story that we sort of arrived at. When you're on a rover team, you don't necessarily arrive at unanimity. It's not a unanimous decision, it's a consensus, and you can disagree with it or not. So here's the interpretation of sulfur-bearing stuff and opal and silica. This is the Kilauea caldera on the Big Island of Hawaii. You can actually just see the rocks among the trees back here. This is called Sulfur Banks, and this is a place, as the name suggests, it's a fumarolic environment where there's abundant elemental sulfur, gypsum, some other sulfur phases, but also opal and silica. And here's rock samples I collected a couple of years later after I was getting funding to go out and understand this problem. These are vesicular basalts that have been so leached, these fumaroles produce sulfuric acid, so there's abundant sulfuric acid in this environment. And in this open system environment, it's so efficient that you can essentially start with basalt, and this is vesicular basalt, and it fully leaches all the cations, calcium, magnesium, aluminum, iron, all go away, and you're left with just opal and silica. So this was the model. This was literally the type sort of model that many on the team, mostly geochemists, and not disparaging them, but in this case, they were sort of focused on the chemistry only to the exclusion of the morphology and the other sort of aspects. And so the first published paper in 2008, I was hoping to be lead author, but the PI of the mission is the lead author in this case. And here I'm going to read this. A straightforward explanation of our observations, therefore, is that acid sulfate, low pH waters, dissolved basaltic precursor materials, concentrating the highly insoluble silica, probably as opal A, there's a story there, and titanium dioxide, probably as anatase. So that was the first published paper. And as is common, the first published paper tends to hold sway for years to come. And here now in 2011, I wrote this tome, 50 published pages and about 30 figures, talking about all sorts of aspects of this. I was using this description, nodular morphology with digitate structures, to sort of capture the fact that we're not seeing nice sedimentary layers of material. They tended to be in these little nodules, and then these finger-like structures that I didn't want to call finger-like, so I called them digitate. So that's the origin story for this kind of nomenclature that you're going to hear more of. So you saw the original picture. This is the microscopic image view. This is roughly 5 centimeters across. And so my interpretation was that these digitate structures, and again, this is in 2011, that somehow aeolian erosion, aeolian abrasion was taking what was otherwise some uniform surface and creating these little structures. That's the best I could come up with. And by the way, I even in the paper left open the possibility, I was at least thinking ahead, that maybe this is a primary texture or morphology, but I wasn't sure. So it's classic geologist leaving a question mark, really. So the reinterpretation started years later with, to me, this is a great story of, I had an alert, for my email to alert me on anything about silica sinter. And sure enough, this paper in a journal that I essentially never looked at before showed up and described this place that I'd never heard of in Chile called El Tatio. And it was the pictures in this paper that just caught my attention. So suddenly I'm seeing opaline silica in this texture. It wasn't exactly a perfect match, but it was like, I've never seen opaline silica like this. This is really interesting. I immediately emailed the She gladly replied, especially when I told her it was about Mars. And so I got email right back from her. And within 5 months, and so we had exchanged some emails. She sent me more pictures. I got more excited. And I invited myself. I said, if I can go along with you the next time you go into the field, I would love to. And so 5 months later, I was in the field at El Tatio. And here's the very first hot spring. As a sort of quick description, this place is at about 4,300 meters at the edge of the Atacama, high UV, very dry environment. This is the most sort of Mars-like hot spring environment that I can find so far on Earth. And if you're into Mars analogs, you try to simulate as much as possible. You know, this is much wetter and drier than colder even than Yellowstone or Iceland or certainly Hawaii, for example. And so, by the way, my rock hammer is here for scale. This is just this small hot spring with a little bit of overflow. These are the outflow channels you can see that barely have any water in them. And I'm going to zoom in. And this was the fourth picture I got from El Tatio. And this picture now has found its way into a lot of places. So here's my real knife for scale. And here are these funny little finger-like digitate structures of opaline silica. You're seeing, this is actually what you can see the glistening of the water. You know, the water is about this deep. All of this dark stuff, that's not dirt, that's microbial communities. And I'm not enough of an expert to tell you what they are, but they have pigmentation to protect against this high UV. And all of this light tone stuff is diatoms. So this is a place filled with microbial life, growing and living and dying along with this opaline silica. So now you can see the compare and contrast at the same scale. And I always like to drive home the point. This is opaline silica. This is opaline silica. And now we've got this remarkable morphologic similarity. It still doesn't prove that this equals this, but it's at least an alternative to an erosion story. You don't need erosion to make shapes like this. Yeah, and here's an even better, more profound, like, so I'm just zooming in on different parts of the scene, but just the similarity in features here is really striking. So now it becomes, is it really, and I don't know, I'm asking this genuinely, can erosion really create essentially the same kind of shapes as something that's forming in a primary fashion? Water. It does have to be in, you know, this is literally hydrated silica. There's a bunch of water, actually. There can be a significant amount of water, and I'm not sure what that number really is, but you have to have water to make opaline, regardless of, and it can form in multiple ways, but there's always water involved. Oh, that's, yeah. So I'll get to the morphology of this stuff anyway on the right. And this is where I brought in my colleague at Arizona State University, Jack Farmer, who was one of the sort of fathers of astrobiology. And his expertise was Yellowstone deposit, Yellowstone hot springs, and interpreting the sort of preservation potential, the taphonomy of the way silica can entomb microbes. So he did all of this important work of doing the thin section work. And here you can see the breccia texture underneath. This is a sample, not necessarily from this location, but you're seeing a sinter breccia silica, chunks of bits of opaline silica and rock. And then over the top, you can see this interesting sort of layered appearance. And here's an even better example. And I'll zoom all the way in to see that literally these are the trichomes of microbial communities that are growing and trying to outpace the silica that's being precipitated on them. So the structure that you see here is a combination. I like to reduce it to. It's a combination of biology and geology that make these structures. And so Jack Farmer, being very conservative, was resistant to jumping to any conclusions until he had this kind of information. And at that point, we could call these stromatolites. So in this case, on Earth in Chile, and it's not unique to Chile, but this is an example of biomediation. So again, biology and geology are essentially driving the formation of these layered structures in these particular digitate shapes. Okay, so here we are with this, profound question of, is this stuff the same? Because if it's the same, then these are biomediated stromatolites. So that was the point at which we submitted this paper in 2016, got 4 reviewers, read it, pushed back, and we managed to actually refer to this as potential biosignatures, and we used the official NASA definition of a potential biosignature, which pretty much is if it looks like it could have been formed by life, but you need more information, that's a potential biosignature, which is what we found. So this paper was published in 2016. The work that followed, how am I doing with time? I need to move along. Okay, so other examples. Here I'm going to use this little identifier of where we're looking. So home plate, we're looking off. Here's home plate. Here's the scale bar. We found this additional example. Martin showed this yesterday. And there's my rock hammer coming in for scale. And so again, my assumption at the time was these are just eroded remnants of something. And then I went to another place. So I went beyond El Tatio. I went to other locations in Chile. Tuja, Chile is hundreds of kilometers away from El Tatio. So this is an example of it's not unique to El Tatio. But here in this shallow outflow channel, are more of these funny nodular and digitate rocks that look remarkably similar to the stuff that we found on Mars. I used my hammer to chip off one of these. And it looks like you could just reach down and pick them up. You can't. They're literally cemented to the substrate. I had to hammer it out, flipped it over, and it sure looks like there's more stromatolites. And being conservative like Jack Farmer, because I haven't done the thin section work, I'm just going to say that looks like a stromatolite. And then, so we're back to this question, are these formed in the same way? These are biomediated structures. And so all of the work here and what I'm going to show in the subsequent slides, we published. You can see Martin and Kathy and Jack Farmer and another colleague. So this was published in 2020. So here's other examples of other opaline silica. We cleverly used, we didn't have any way to manipulate these rocks, but we could use the wheels of the rover. And when you tell a rover driver that we want you to drive up to something and wreck it, they get excited. It's pretty fun. So here's this place that we disturb these rocks. These are all, to the mini test instrument, were all opaline silica, so we knew that ahead of time. And here's a texture that I published, and Jack Farmer, knowing what a sinter breccia is. A breccia, it just means it's a bunch of bits that have been cemented together. We could recognize this breccia texture and samples from Chile, from El Tatio in this case, same scale, same material, same textures, remarkably similar. This is a different style of silica sinter deposits. It's just broken up versions of the other stuff that gets re-cemented together. I was interested in here's a surface that we looked at close up, and that's a sun glint over here. But this texture looked quite different than this. But my hypothesis was this stuff has been sitting, being sandblasted and eroded. So I actually went to the effort of getting a sandblasting lab set up where I could go and take rocks like this. And now here's a piece of sinter breccia from El Tatio after sandblasting, same scale as stuff that was sandblasted. And you can even see little details like these tabular clasts that are part of the breccia, and there are examples here. So sandblasting a sinter breccia on Mars, if it's sinter indeed, can give you that sort of texture. So this question about the relationship between the sulfur-rich material and the silica-rich material, and here we're looking off to the east of home plate. This was something that really came into my understanding much better with a field area in the western US in Utah. You can see my vehicle over here for scale. This is a geothermal power plant, basically at the other end of these pipes. And so this is a hydrothermal system that's still active today. But in this case, the water level has dropped and there's extinct hot springs up on the top. So after the water level dropped, the hot springs dried up and there's still active fumarolic activity down below. I stopped at a place up on top, and here's a dried up now, probably more than a century old hot spring. And I literally just put my backpack is over here. After I set it here, it was still, my backpack was hot. There's actually, this is now a fumarolic environment where there's literally elemental sulfur produced from the plumbing system that used to provide hot water for a silica sinter deposit. And on the rim was a bonus that the texture of this particular sample on the edge of this hot spring sinter, I suspect might be this sort of funny sponge-like texture. And that's the phrase that I used back in 2011 for one of the deposits. This is Elizabeth Mahone again. And that texture that I described as sponge-like, I didn't have an explanation for, but now this is a candidate explanation that this whole hot spring system, if that's what we're looking at, was overprinted on Mars by later stage fumarolic activity. The last thing I'm going to show is this feature that we didn't get to because Spirit died before we could get there. And so this funny mound that we refer to as Pioneer Mound for some reason, you can see the scale bar. This is just off of home plate, a few tens of meters. The final Spirit resting place is right here. Spirit got trapped in regolith after one of its wheels had died. So we were within a few tens of meters. We've got mini test observations, but they're just at the edge of sort of the quality of them. But it looks like, based on the color, the morphology, and the mini test spectrum, that this is more opaline silica. And why is this important? It's because elsewhere on Earth, there are exactly sort of the same kind of morphologic features associated with hot spring systems in these different places in Chile. These are hot spring vent mounds. You can see this one is now dried up. This one's still flowing. This one's dried up. This one's still flowing. So this is a characteristic shape, including even this sort of rim at the top. So we're left with this question: is this literally a hot spring vent mound that we could go visit today? And wouldn't that be cool? All right, so that's the last, and the quick summary here is, and this is where I come back from geochemistry is great, but you really have to incorporate all the observations that you can make. It can't just be a story about geochemistry. You need these additional features to really interpret what you're looking at. We need geochemistry, but we also need geologists in geology, right? Okay, so all of this suite of observations, including the terrestrial analogs, just really builds this very strong case that what we found in this place is not only a hydrothermal system with fumarolic activity, but likely also hot spring activity. And the rocks, so this sort of pure opaline silica is best explained as hot spring deposits, not by acid sulfate leaching. And the last thing is that these structures, these digitate structures, are actually potential biosignatures by an official NASA definition. So wouldn't it be great to go back there? We've left unaddressed this profound question. At the time, we didn't know what we were looking at. It took years to uncover this story and come back and say, we may have found potential biosignatures. We didn't know that at the time. So we need to go back. That's it. Thank you. From the other rovers, no.
Oh, so that was very specific to this
Yes.
place.
Yeah, wouldn't that be nice? No, this is a very unique spot on Mars, and it truly was just absolute fortuitous luck that we stumbled across this. There was no planning to go look at hot springs in Gusev Crater. We went looking for an ancient lake. We didn't find the evidence of an ancient lake, and we just stumbled across this other thing. And no other rovers have seen something like this.
Great talk. Thank you for the amazing images. So what analysis, if we ever go back to the same spot, would you require to convert potential biosignature to actual signatures?
Yeah, great question. So, because the other definition is definitive biosignature, and there's a NASA definition for that too. Martin and Michael and I and others, we assumed that you would have to bring it back, bring sample material back to prove definitive biosignatures. But you could go a long way with just another in situ mission. For example, looking for those layered structures. You know, I showed you that we at least tried to break break part of that open, but it turned out to be that's the wrong place to break open. So if we could go back and look at a broken version of one of these digitate structures, and if you had some ability to look for organic matter, I guarantee you if there's organic matter, it's going to be degraded. It will be reduced to some very, degraded version. But think of the significance of finding a little digitate structure with even kerogen, type of organics in it. So looking for organics in these rocks would go a long way. And then to me, this other aspect, the Pioneer Mound as a potential intact hot spring mound would be a great place to go now, looking for other textures that signify the presence of microbial life. So that combination of looking for organics in these structures and looking at this like candidate vent mound would be what I'd want to do there. Raman, but FTI IR works. I'm starting to really appreciate IR for organic detection as well, if you have the right wavelength. Yeah. Martin.
Sorry, I'm sprouting for Mike here. He's going to show that there are sort of chemical biosignatures in the way that microbes concentrate trace elements. So that's another aspect that we could look for together with the organics.
I have a quick question. So can you distinguish between Opal A and Opal City?
Yeah. Yeah. So in IR, there starts to be sort of changes in the shape of those major, especially at long wavelengths. You start to see some change in shape. I haven't quite convinced myself that all of the opal that we saw was still as Opal A. There's some potential that it's gone a little bit through the paragenetic sequence into Opal C or CT. The most important aspect is it hasn't gone to quartz, because once it goes to quartz, and maybe someone will correct me, but that the textures that are so important, those textures are not going to be preserved if it transitions all the way to quartz. Mike so this is why I'm equivocating.
Yeah, the reason I asked it is because, so are you suggesting that these are primary precipitates out of a supersaturated silica solution, or could these have some precursor material? Because you mentioned life, right?
Yeah.
So in general, when you have certification, you need a precursor. Sometimes there's a limestone which has been certified.
No.
You can have volcanic ash which can be certified.
Silica hot springs, literally, if the plumbing system of that hydrothermal system is going through silicate rocks, the chemistry and temperature, the conditions are sufficient to liberate silica from silicate rocks, keep it in solution until it gets to the surface, and the combination of cooling and evaporation, it doesn't even have to be super saturated in silica. It just needs to cool and evaporate to then generate. Those are chemical sedimentary precipitates. So I think does that answer your question?
The reason I'm getting to the geochemistry side of things, because I think if there's a precursor, there are ways to figure that out, because the chemistry of that opaline material is going to be slightly different.
The trace element chemistry.
That's right.
That's fair. Yes. All right.
There's one additional feature which I don't think I'll have time to talk about, but importantly, and Steve and the Spirit team have also pointed that out, is that the rocks that sit beneath the opaline silica have been affected by acid sulfate alteration. And the rocks that are directly above the opaline silica are fresh as a daisy, absolutely unaltered. So that actually goes to pointing to that environment again, where those hot acidic fluids have affected the underlying rocks, but then the subsequent volcanic event came afterwards. So contextually, there's additional information that strongly supports a primary deposit of these silica deposits. And interestingly too, no other rock type in that area has that kind of digitate weathering structure, and it's unique to those opaline silica rocks. So that is another argument to say that it's not because of aeolian weathering or something. It's a unique feature of that particular rock type. So there are a couple of extra, contextual observations that are really important.
Steve, yeah.
Yeah.
Just a continuation with what Professor Ramananda said. We were talking about the opaline silica, and mostly in astrobiological perspective, it can indicate the wet-dry cycle, right, also. And not exactly silica, but the other minerals like the halides we get many places. So that can suggest you. So is there any other geochemical proxies to identify in a fossilized hot spring system? So if, geochemically, can we characterize the wet-dry cycle?
I think that's a good intro to Mike's work. So, so this is a place like El Tatio. They are alkali chloride waters that, in more wet environments, the chloride is wet. It's halite incrustation. So the last thing to come out of solution is halite. And I learned it by tasting it, but I had to use SEM. I couldn't put it in my science paper that I tasted it. I did know on top of the SEM and EDS work. But yeah, there's halite, and spectrally, the stuff on Mars, there's a feature that I couldn't interpret until I brought stuff back from El Tatio, the halite. So the Mars version appears to have halite. So it's silica and halite.
Yeah.
Right.
So hot springs, that's its own.
We should start with.
Thank you again. And so we'll move on to the next talk by Michael Rowe. So please take over.
Okay, well, Steve's done a great job of setting me up for this, so this will be quite straightforward. So I guess my job coming in here now is to kind of start picking apart how we might be able to identify life in these materials, again, based on the model that these are somehow related to a hot spring environment. So my background is as a geochemist. So I've been brought into this kind of specifically for this purpose of trying to identify different ways that we can try to look for evidence of life in these rocks. Kathleen Campbell, my friend and collaborator here, has contributed to this talk as well. And we're going to kind of paint an overview picture of what we would recommend for approaches and why we would actually kind of make that recommendation if we were to revisit this site. I'd also like to point out, Steve made a great case for the amount of information that's been learned since the original discovery in 2007. But I want everyone to keep in mind, it's really common for a geologist to go back to a field location after they've done additional work and get new information with new instrumentation. I mean, we learn through iteration often with our science. So there's no reason not to kind of consider that option as we go forward. This is just an example of one of the hot spring samples that we'll look at here shortly. So this is a pretty big research team. Steve, Martin, and a bunch of other people are involved here. And I want to highlight this from the start because really we're working at the intersection of hydrology, engineering, biology, chemistry. And so it does require a wide range of expertise to actually try to kind of think about this intersection of life and rock here. So we have had a lot of students over the last few years. Right now, we're focused more on the chemistry side of things. A couple of years ago, we were focusing more on the mechanical properties for these materials. So I'll try to kind of bring all of that together in one story for you here. I'm going to split this up into kind of two parts for the talk. The first is I want to kind of make this case thinking about analog environments and the importance of actually mapping out our observations on the surface here and correlating these analog environments to what might be present on the surface of Mars. So that'll be kind of the first part of it there. And then the second part will step into actually then, all right, well, if this model is correct, how can we try to identify life in that? And I'm going to continually make the case that no, as Steve said, no kind of single piece of evidence will definitively give us evidence of life in these ancient rocks on Mars. All right, the best case scenario is for sample return, but there's also a lot that we can do by, again, combining these multiple different approaches. I'm going to try to make the case that what we need is a combination then of the textural, organic, and inorganic evidence. So 3 different kind of independent approaches to try to get at this question of biogenicity in these rocks. So again, we've seen this picture before, highlighting the importance of the textural observations on Mars and on Earth. And I just wanted to kind of make this point about the terrestrial analogs and the importance of our analogs are only as good as the information that they're based on. Steve, again, showed a great example of how that initial interpretation was of acid sulfate alteration. And so they started looking at analog environments that would fit that scenario. But through continued work, the model evolved to something more along the lines of the alkali chloride systems that we're thinking about now. But that's not to say that model won't change again in the future as we continue to get more and more information. Yeah, so again, the spectral comparisons along with the textual observations there. So why is the hot spring environment so important? The 2 kind of main reasons to think about this is first, the preservation. In hot spring environments, we get abundant microbial material preserved, rapidly solidified throughout the deposits, from high temperature at the vent, up around 100 degrees, all the way down to the low temperature marsh settings. And all that material then gets solidified or silicified into this material. And I'll bounce back and forth between silica and sinter in my terminology, I apologize. The other aspect of this is that this can be predictive. And that's where this becomes important, thinking about the mapping out of these environments and using these terrestrial analogs to try to kind of understand the distribution of these materials so that we know where we might want to go back and look when we're looking at the surface of Mars. So this is a model that's been in the literature now for 14, 15 years, I think now, thereabouts, that looks at the change in the environments in an alkali chloride system, again, from vent to the distal apron here. And the important aspect that we have life and we encounter life in slightly different forms in all of these different settings. We can see we get bubble mats, we get these conical tufts, streamers, deep pool stromatolites, but all in a very systematic pattern. Again, we get the high temperature settings up here where we'll see different morphologies and different microbes than what we see when we move out to kind of the conical tufted or out into the palisade fabric further along. So the environment changes depending on the temperature conditions that we're under, and of course, depending on the fluid conditions that we're under through here. Oh, yes. Well, that's the next slide, Martin. Oh, not quite the next slide, but it's coming, I promise. Steve's made this point about the digitate materials being very similar to stromatolites. And we can refer to them. I know he hates it when I use the term digitate to describe these. But all of these are essentially microstromatolites. They're built up of variable, sometimes silicified microbial material, oftentimes a lot of detrital material, and then interlayered with these, we'll call it smooth or solid silica here. And we can see that, again, with the white layers that make up each of the individual layers of this microstromatolite texture. So again, layered material, microbe minerals, we get this positive relief. Again, we've talked about or Steve's talked about kind of that buildup of the structure. And again, importantly, we're entombing that microbial component within the silica throughout these materials. So we have this enhanced preservation of these materials. So So here's some work done actually by one of Kathy Campbell's students, Kim Hanley, back in 2008, looking at experimental growth of these small digitator microstromatolite materials in Champagne Pool in New Zealand. So this is what the deposits look like in the pool here. And again, we can see in this case, they're a bit pointier than the ones Steve was looking at earlier. But what this research really highlighted is that every component of this actually is in some form organic. All right, we've got the more obvious silicified microbial filaments that make up this layer here. But this upper layer, that material I was calling smooth silica or solid silica, is actually silicified EPS, exopolymeric substance. So it's ooze or slime from the microbes. And this ends up making these, and I apologize if there are any microbiologists in the room. I'm not a microbiologist, so my terminology probably is not correct here. But it makes these then smooth layers that we see spread out in between either the detrital or the microbial content. So these are organic structures, even if we can't really see the microbial material mixed into them. So here's the slide Martin was waiting for. Just an example of where we see this digitate material. Again, we can see it in the more distal apron here, or we often also see it in kind of that mid-channel region where we have, again, a slight cooling, slight overflow of water. As Steve's already mentioned, these tend to form at the air-water interface. So it's, again, it's a combination of buildup of this organic material with a wicking process for the water. Now, there are similar microstromatolites that form right up near the vent that are referred to as geyserite. These have a slightly different structure to them, and I'll show a picture of this for comparison a little bit later on. But these tend to be very localized around the vent and much denser compared to the more distal materials. So going back to this idea of why do we care about mapping? Steve just showed this example, which is great. We've got the Pioneer Mound here and an example from Chile here, thinking about the vent location. And we can think about this in terms of being a very basic geologic map of the surface of Mars. Right? We've got Pioneer Mound circled over here. We've got dashed lines around some of the silica deposits here. I haven't identified, we haven't identified where the sulfur is, but again, it gives you an understanding of the distribution of some of this material. All right, so if we go then and start applying this same process to our analog models, we can start thinking about where we might want to look and how we can start to explain some of these observations. So this is an example from Tikitiri in New Zealand, where we had a PhD student. This is actually her honors work in 2018, but mapping out this deposit. Now, again, we've got the aerial shot over here on the left, and you can see a couple of very distinctive pools, and we get some hot springs kind of draining out in different areas through here. We have our digitate material, again, a more what's referred to as a spicular form, more needle-like form here. But let's take a look at the geologic map here for just a minute. So in red is the area where we see kind of this, what we'll call rotten ground, where we've had a lot of dissolution from acid sulfate fluids. In yellow is where we actually have little sulfur mounds and sulfur being deposited. But at the same time, we're having that sulfur deposition and that ground being eaten away, we're having the buildup and the precipitation of spicules. So all this stuff in green are the areas where this silica is actively being deposited. So we're having the buildup of these digitate features at the same time we're coexisting with the dissolution of this material. So Steve showed a version where we were looking at Roosevelt Springs and you had an alkali chloride system that was being overprinted by acid sulfate. Here we've got both of these coexisting. And if we think about then the spatial distribution, this is a very nice model to think about how we can have that coexistence of the acid sulfate deposits with the actively precipitating digitate material. Here's another spring, a little bit smaller this time, same general area, but we have the nice hot spring here with a pool, no mound in this case, but two different outflow channels. And this one contrasts from the last one. We don't have the acid sulfate alteration here. This is more typical of a standard pool, mid-channel, distal channel, or distal apron deposition here. But it allows us to be very predictive about where we see those different morphologies and those different biological components showing up here. And importantly, we can see, again, we can see streamer fabric, the conical tufts, we've got terrace fronts. Let's see, I don't know the pink here is our digitate center. So in this case, our digitate center is in that kind of mid-temperature range on both of these. Again, a specific temperature range where it's occurring, a specific distance from the vent. So we can use these basic models then from mapping out these analog environments in detail to then starting to think about how this can be applied for when we were going back to look at Mars. So again, I just want to reemphasize that the main point here is the importance of not just using the analog sites, but really mapping them out and then portraying that into the Martian environment. Okay, so I want to step now. We're going to work on the assumption that these are silica deposits and that we're dealing with microstromatolites. So from there, I want to start thinking about how do we actually try to identify life in these materials. And as I said from the start, we're going to take a look at 3 different examples. We're going to look at the textural evidence, some organic evidence, and some trace element evidence. So we'll start with, I've taken to putting this image up in talks. I actually really don't like this image because I tend to work down here. I never get very high up on this ladder of life detection. But it really drives home this point of the importance of having multiple independent lines of evidence. Because when we're dealing with the ancient rock record, we're never going to get to Darwinian evolution, right? So we're not going to progress very far up this ladder. The best we can do is move laterally and have multiple different lines of evidence. Okay. So starting with the physical characteristics of these materials. Steve's already showed this figure on the left. Here's an example from a place we named Mars Pool because of the similarity in the digitate texture here from Rotokawa in New Zealand. But again, the same sort of digitate structure here. And importantly, if my colleague Kathy were here, one of the things she'd focus on is the idea of these branching structures. And that's the point that she continually makes, is that these branching features are much more indicative of these digitate structures that we see in the modern hot spring systems. But again, a nice spatial comparison, same scale, same sort of underlying more vesicular material. Note that we don't see any of that microstromatolitic texture when we look at these, right? We just see knobs. So, it's great to have a form, but it's not necessarily indicative of microstromatolites at this point. So there are actually a wide range of different textures that we see for these digitate features, and they've been defined based on their aspect ratio. They can be knobby, they can be spicular, but they all tie to different paleo-environment conditions, different fluid chemistries. And I'll come back to that in a couple slides when we get to the organics. And here's that same sample from Mars Pool. You can see where I kind of took that blow-up picture. We've got a couple of samples, a little more rounded here, really blobby material here, and then much more spicular deposits. Again, these tend to form in our more acidic conditions here. I'm going to take a look now in much more detail at just this one spicule. Now, these are micro CT images. So we took one from that. This is that one that I circled in the yellow box. The one on the right is one that Steve donated from El Tatio. See if I can get these to play. One, here's the other. Okay, so as we start looking through them with the micro CT, now we can see that internal stromatolitic structure. This is basically a density map. We can see the dense layers, and then we see that the purple here are the lower porosity zones. You can even see some of on the one on the right, you can see little bright spots of the phytal quartz that gets incorporated in from the aeolian processes here. So again, very characteristic draping structure here. We don't see the organic material at this resolution. This is about a 1 to 1.5 micron pixel size here. But it gives us a good overview of that internal laminated structure that's very characteristic for these digitates. So even if we don't see it on the exterior of the samples, there's good evidence to suggest that we'll be able to see it on the interior using a different technology. Now, here's just a 2D slice of that 3-dimensional image here showing the porosity now that we've extracted from that. And the reason I want to kind of step aside and talk about the porosity a little bit here is that one of the things that got me started on this was thinking about, okay, well, if we are going to try to sample this material, how are we actually going to do it? Right? These are irregular shapes, and they've got odd properties to them. If you were to just break a piece off of this, you might get some random slice without really capturing that stromatolitic texture. So how do we go about sampling it? For my part, to help address that, what we were looking at is what are the mechanical properties, what are the strengths of it, and how can that then impact how we can do the sampling. So in addition to the micro CT, we went through and did nano indentation on the surface of this basically to measure thousands of little points to understand how hard the material is. And not surprisingly, there's a wide range of results, right? S plus P is silica plus pore space. So in the more porous domains, we can see it's softer material than where we have our solid silica. Again, not terribly surprising. The solid silica is harder than the more porous silica. We also have a range depending on the type. Here's hardness down on the x-axis, depending on the type of the material or where it's being collected from. This becomes important again when we think about how we're actually going to sample this material. Right, the worst case scenario, if this is what you're targeting, this is what you want to go get, to get there and not be able to collect it would be the worst case scenario. So when we're thinking about sampling, we have to think about how we can prepare for material that might be out here and really hard, or might be out here and be really soft. We have to be able to cover that range. So in 2022, we had a workshop out in New Zealand, and we brought some Japanese colleagues who were working on different sample collection devices, and they'd construct a little chisel to try to start thinking about how to break this material. What you're not seeing is that there are about 7 geologists just outside the field of view, everyone with their cameras filming this. We'll just start it here. So nice slow motion. You can see it goes through. There's one nice digitate piece there that's spiraling out of control out of the field of view. Another one that's coming to a stop down there. But as Steve said, you know, the example from El Tatio, this stuff was really hard. It had to be chiseled off. The same is true for this locality. You can't just go out and pick them up. Now, 10 meters away at another pool, you can just go and pick them up. So again, how these are cemented down is highly variable depending on the conditions that you're in. And you have to be able to take that into account when you're doing the sampling. Okay, so we'll talk a bit about the organic biosignatures now. Again, coming back to the point, we've got several different types of digitate here with different morphologies that are somewhat correlated to the change in the fluid chemistries. So we've got our alkali chloride. This is similar to El Tatio that Steve was showing examples of earlier, but we still see these digitate structures showing in acid sulfate chloride, and acid sulfate bicarbonate fluid. So wide range of fluids, but all still giving us this kind of digitate morphology. The important aspect of this is life is present in all of them. Right? It's a little bit different, but it's present in all of them. So again, here's the SEM view of some of those features. A close-up, again, showing that microstromatolitic texture. In some cases, it's easier to see. In others, depending on the porosity of the sample. And then some evidence of the different, different microbes that are present in those same materials. All right, so life's present in all of them. Now, don't worry about the details here because I don't understand all of them either. But we've got gradients for temperature up across the top here, variations in pH, and variations in different types of water. Again, all I want to make, the only point I want to make with this is that we get a lot of diversity of microbial material. But again, microbes are present in all of it. The cyanobacteria that Steve was showing, that was kind of the green stuff around the El Tatio sample there, is kind of this orange color. So we see that in the alkali chloride, and that's a dominant microbe in the alkali chloride, and a little bit in the alkali chloride or the bicarbonate springs through here as well. But we don't see that present in the more acidic conditions. Right? It doesn't like it living in the acidic fluids. But we do see other microbes kind of step in and fill that void space. So again, this comes back to why this is such an important target, is that everywhere we see these forming, at least on Earth, they always have life preserved in them. We talked a little bit, Steve talked about the spectroscopy. Here's an example looking at ramen. So again, looking at El Tatio here, you can see the nice filaments here for the cyanobacteria, and you can see the kind of, hopefully you can see it, the orangey brown coloration of the individual filaments here. So this is the pigments that are preserved. So these were the scans that our student did looking at the pigment and identified, again, two different key chemical components present in the pigments. Now, the challenge that we encountered with this, this is the best example. Ramen actually turned out to be very, very challenging on these materials. With hydrated opaline material, what we end up seeing is a lot of fluorescence. And it causes a lot of problems, especially with the blue and green lasers. We went to a longer wavelength laser here, which meant a single analysis might have taken 5 or 6 hours to collect. So we knew what we were targeting. We went and spent a lot of time to try to get the best signal. But it highlights some of the challenges with the different types of material and trying to get it, trying to get some of this information out of it. I will point out, when you start going to materials that have started to go through this paragenetic sequence that Steve was talking about, transitioning from Opal A to Opal CT over to quartz there, we start to drive out some of that water, and as we increase that crystalline structure, it gets easier to do the Raman analysis. Unfortunately, if we're really targeting that Opal A material, that's the worst case for using the Raman. Looking at just some different microbial approaches here, or molecular preservation. So this is an example, and I won't get into details here, but looking at late Jurassic deposits from Patagonia. So here we're thinking about 160 million years old. I'll show a picture of this at the end or towards the end as well. But looking at the molecular biosignatures, this is, again, an example where this material is very well preserved. Steve made a comment that if we go and look at this material on Mars, most of the organic biosignatures are going to have degraded into some smaller organic components. This is like a good exception to that. This material has transformed all the way to quartz, but we still are preserving the organic components within it. They've looked at, again, Raman mapping at this and showed, looking at geyserite structures, you can see the organic material still lining those. One of the issues here that they think might contribute to this good preservation is that these materials, despite being 160 million years old or so, never went through a significant amount of burial. So they didn't progress, we didn't have high temperatures and pressures as these materials were buried through time. So this might be actually an interesting analog for thinking about the Martian stuff if that stayed near surface for long periods of time. All right, so I'll talk about kind of the trace element work, because that's in this last step, that's a lot of what we've been focusing on for the last year or so. There are a lot of different trace element biosignatures out there. Now, most of these, I don't know if you noticed on the last slide, I put metabolic in quotation marks, because I'm not entirely convinced that they're all actually metabolic, but we can discuss that later. But there are a lot of different types looking at trace elements or at isotopic ratios to try to correlate them to, again, biological processes here. Most of these then, again, are unique to their relative environment. So for the rest that I'm going to show, I'm going to focus on one element in particular, and this is the work we've been doing on gallium. Now, gallium's an interesting case. It's toxic to microbes. It's not really a necessary component for anything that they do. But it has a charge that's very similar to iron 3+, and it has an ionic radius that's almost the same as iron 3+. So there are a lot of studies out there, in particular in the biomedical world, looking at it as a potential antimicrobial agent, because the microbes pick it up thinking that it's iron 3+. So even though it's not necessary for life, there's a potential that it can be incorporated because it's mistaken for iron. So here's that El Tatio example again now, looking at the microbial filaments. And here's just an example, so you can see these cyanobacteria filaments here. And the structure that we're looking at is we've got the trichome through the middle and then this sheath that's surrounding it. We very rarely see evidence of this trichome preserved through the silicification process. Most of the time, what we're seeing is actually the silicified sheath that's around it. And we see that then with the chemistry. It's a little hard to see on this example. I'll show a better one later. But most of the enrichment in gallium actually occurs right along the margins of the microbial filaments, not all the way through them. Now, for this to work as a biosignature, we'd hope that it'd be more widely applicable. So we've looked at a range of different locations. This one's, as I said, from El Tatio. The other point I want to make with this, so Steve showed that image of the samples in the field, and you had the white knobby material sticking up, but you also had the material. The green here represents where we're seeing gallium, and that's where we're seeing a lot of these microbial filaments being preserved. A lot of this material, again, is this classic stromatolitic texture. We can see the nice layering in it here, but we don't necessarily see the same biosignatures showing up in it. Again, this comes back to one of the potential challenges that we have to deal with is that depending on what we sample, we may or may not actually get a good piece that shows the ideal textures. Just this last year, we went and worked at Yellowstone, and these are some of the samples from that. Here, we've actually got a conical tuft, so this is a mid-temperature range with palisade fabric growing out of it. So we're actually capturing, in this example, the change from mid-temperature to cooler conditions in the growth. But again, we can see that same enrichment of gallium on the margins of the microbial filaments. If we zoom way in on this, we can now really see that gallium enrichment right along the boundaries of those microbial filaments, showing that it's really that sheath that's being silicified here, rather than the trichome and the sheath and all of the material in between there. But again, very, very characteristic, not necessarily a biological process, but it's certainly tracing a biological process in this example. Now, they're not always that simple to interpret. So this is an example, or two different examples from geyserite. So this is that high temperature stromatolitic material here. Again, this material is still templated with life. Our solid silica layers are still being built up from EPS. But we don't necessarily see those nice elongate filaments with the easy to interpret textures now. We can still see, again, the stromatolitic texture here, and we see high concentrations of gallium involved kind of both in and around these features, but it's very challenging to figure out which part of this is life and which is not life. So for this reason, and I won't get into all the gory details later, but we've done a lot of different types of analysis on this, trying to now pick apart this. We've developed routines for doing gallium isotope analysis on these materials to see if we can see biological fractionation. We've taken these apart and done Zane's analysis to look to see how the gallium is bonding with other components there. So there's a lot of background work trying to kind of interpret how these materials are actually growing and which parts of this are biotic and which are abiotic, if you can actually tell those apart. Stepping back in time a little bit, this is 16,000 years now. So this was an Opal CT example rather than a nice Opal A example. We can see it's a little bit blurrier, not as quite as clear an image, but we can still see those nice microbial features here. Up in the example up here, you see little circles. There you're looking end on these filaments. So you're looking down the length of it, down the tube. Here we're looking at cross-sectional views. To give a slightly better view of that, we did some higher resolution scans. And now we can see, again, looking right down that hollow trichome, and you've got your silicified sheath around it with those high gallium concentrations. Again, the cross-sectional view here showing the long axis for these filaments. We can go back in time a little bit further. This is that same location, Claudia in Patagonia, where they were looking at the molecular biosignatures. Here, again, we can still see our filaments preserved with those high gallium concentrations. Again, not as clear as the Opal A. So this is Opal A, Opal CT, quartz. Now, again, I've shown the best example here for the quartz. Once we get to there, it really is very preservation dependent on whether or not we're going to see those biosignatures. But we can see in each example, and I've just done a transect across two filaments for each of these. that we still get that enrichment in gallium that's very characteristic for these materials. And just to kind of go one step beyond, so now we're working on a technique to actually start imaging this three-dimensionally. So anyone that's familiar with the idea of tomography, it's a way to look through the sample and map out the chemistry, but you have to have a very distinctive, you're basically dealing with cylindrical samples, which does not always lend itself well to geologic materials. So we've been developing techniques to look at flat materials like a thin section or a slab of rock in 3 dimensions. Now this was our experiment. We redid this a week ago. And I don't yet have the nice process images. So this is last year's example. But you'll be able to, as I rotate this through, this is now a map of iron. You'll be able to see the filament traces kind of going through the sample as we rotate that around. So again, it's essentially looking at something equivalent to a tomographic image, but of a flat surface here. So the experiment we ran, I guess we ran it starting on Tuesday last week, a single analysis we ran for 3 days, trying to just get the best imaging possible to try to reconstruct this as a proof of concept. But it's, again, pushing the boundaries of trying to find new ways to identify these potential biosignatures in this material. But yes, so this is a synchrotron radiation. So yeah, very, very high spatial resolution is necessary for some of these, but it's all X-ray technique, yeah. So what this is doing is we've got the sample at it's actually like about 44 degrees to the X-ray beam. And the sample is rotating. So we map it all out. We rotate the sample a little bit, map it again, rotate the sample. So we keep rotating the sample. So the volume of material that the X-ray is interacting with changes because of that incident angle. So you then have to piece all of those different images back together to reconstruct that three-dimensional. Yeah. Yes. Yeah. Yeah. So it all depends on the angle at which you're hitting the sample and then rotating the sample around. I will admit, I'm just the geologist on this. We have a physicist that's actually doing all the math for this. That's beyond my capability, but it's still really exciting to see what we can do with it. Now, I wanted to come back to that issue of the guys right here real quick. Just think about how we can start to say something about the environment that they're crystallizing or that they're precipitating from. So here, again, we can see a nice thin section view of this stromatolitic texture. Here's the elemental map that goes along with it. Red, green, blue is just gallium, arsenic, rubidium here. So this is our gallium-rich area. We also went through and did micro X-ray diffraction on this so that we could take a look at the individual growth domains, again, to think about the environment that it is growing from. And what we found is that when we systematically looked at this laminar region, we saw a different mineralogy to where gallium was growing directly over the top of it. Here we saw, in this case, opal A, but also in this example, a little bit of fluorite. We also sometimes saw a little bit of calcite. But whenever we looked at the material over the top where we have the higher gallium, it's just the opal A. So we actually have a change in depositional environment as we're going through these different samples. What that means for life, honestly, we don't know yet. This is still relatively new data and we're working our way through it. But again, it's showing how we're trying to bring together these different parts of the story here. And I think the important point to drive home with this is that if we were just analyzing this without any other context, we wouldn't get anywhere. We have to have that geologic model and that paleo environment reconstruction to really have an understanding of what it is we're seeing here. Which these? So each of these striations are one of those individual lamellae that we see for the microstromatolite. So it tends to be, again, it'll be that denser silica with maybe a slightly more porous silica in between there. With the guys, right, most of these are pretty dense layers. Basically what you're seeing is materials being splashed out near the vent. So it's getting a water added to it, and then it's evaporating away, and we're seeing that precipitation. So it's showing the cyclicity in that splashing action in that near vent region. Yes, so this uses scanning, and we'll, make individual measurements kind of across it. Yes. Okay, so just to kind of wrap all this up now, I could spend forever showing you great pictures, but it's a lot of fun to collect this data because you get to just sit there and watch these amazing images come out. But again, whether or not we're talking about some sort of a rover-based mission or a sample return mission, right? In that context, it doesn't matter. We need to have multiple different lines of evidence if we're trying to prove ancient life in these old samples. So again, the recommendation, the mapping, so that we have some sort of context to interpret the samples and the sample locations, textural analysis, again, the high resolution imaging, but also hopefully being able to look at the interior of these samples, whether or not that's you breaking the sample open and doing imaging of it, or development of micro CT on a miniaturized scale, allowing you to look inside the interior of those samples. Something for doing the organic biosignatures. Again, Steve's talked a lot about FTIR or spectroscopy. Raman obviously works, but has its potential limitations. Trace elements, again, pick your choice of instrumentation that can do trace element analysis. But again, the importance, I think, is the ability to do the high resolution trace element analysis. A bulk analysis, as you've seen from the diversity of the materials, will tell you what's there, but it's not going to give you that spatial context that allows you to correlate it to the textural observations. Yeah, so you need something to be able to match that texture that you can see macroscopically or microscopically with the chemistry. Yeah. I think that's just unfortunately going to be a problem with hydrated opal and trying to do Raman analysis on it. Too bad, it has a lot of potential, but and yeah, again, just that last point, the samples are heterogeneous. We need to be able to take that into account and look at the high spatial resolution. Okay, so I'll stop there. Thanks.
Questions for
Mike, it's a very nice presentation, I must tell. Now, I know nothing about biology, okay? So, but from my, college days when I studied stromatolites, I think I remember someone telling me that the growth of stromatolites are controlled by sunlight. So towards the direction of the sunlight, these colonies grow. And as they grow, they form those films and rings and all, the colonies. Now, has any, to your knowledge, has any experiments been done on these sorts of opaline silica without sunlight, whether they will produce these similar structures mimicking the stromatolites, what you call microstromatolites?
There are groups working on abiotic, trying to reproduce some of these textures. In fact, we have a microbiology student who's doing microbial growth experiments at the moment, and also doing some abiotic silica precipitation, trying to grow that. We haven't done without light because most of the microbes that we're using are photosynthesizing. So obviously, without the light, they wouldn't grow. But the geyserite material, those are too high a temperature to have photosynthesizing bacteria in them. Because those are typically in that anywhere from 75 up to 95 degrees Celsius. So those ones are growing from that splashing action and drying. I can't comment about whether or not they would always grow towards light, but we do have examples where they're growing upside down and in different directions, kind of depending on where steam and fluid is at as well.
Can I just add to it? There have been experiments where a light bulb is put underneath the stromatolite and they still grow upwards. The upward growth is more a feature of free surface than it is necessarily of phototrophy, because the microbes want to maximize the surface area that they can grow. So if you have a two-dimensional plane, you'll limit the amount of growth you can have. But if you start making that surface rough, you increase it tenfold. And so, as Mike said, and the guys are right, you get the same positive growth structures, laminated growth structures, but it's not by phototrophs. But it's the life is making surface available for itself to grow. That's the key point. And so now they know that these stromatolites can be made by chemoautotrophs or by photosynthetic or by anoxygenic phototrophs. Doesn't matter. The consortium changes, but the growth pattern is a free surface problem.
Hello. Yeah, so actually, I have a very quick question about homogeneity of the samples that you're doing geochemical analysis with. Since we're drawing analogy of samples of the Earth with the samples that you're bringing from from Martian samples, I'm just curious to know that how are we defining the homogeneity of Martian samples, the geochemistry of Martian samples?
Well, at this point, we can't. I mean, the best we can do at this point is study a wide variety of terrestrial samples that we can understand basically what are the limitations on different variables and what that means for what we might interpret. We're trying to set boundary conditions basically to understand the region.
So I want to ask, what's the best possible homogeneity that I can define for Martian samples?
Well, morphologically, a lot of the stuff that Steve has shown from El Tatio, again, high altitude, dry, alkali chloride solutions, give us kind of some of the best morphological comparisons. Again, in terms of comparing to Mars, really we're limited to opaline silica and the morphologic features, right? The rest of it is we're just saying, all right, these are, again, as I said, the boundary conditions for those experiments.
Hi, thank you so much. It was an awesome talk. So I was really fascinated about the gallium part of your talk where these microbes would potentially take up gallium in comparison with iron 3+. And I wanted to know whether, first, what is the reason of gallium in these hydrothermal vents? I do not know, sorry. And second and I think you briefly mentioned, probably someone is doing some stable isotope probing measurements, and what are the results if there are any?
So for stable isotopes, we see about a 4 per mil fractionation in the biological material compared to the silica that's around it. So it's about 4 per mil on average lighter. It's highly heterogeneous. So we'll try to do an analysis right on one of the filaments and then something that's immediately apart. Those tend to have a nice isotopic distinction. But if you go to the next pair, there'll still be a distinction, but they're going to be different from this pair. So there's it's a technique that we're right at the limits of what we can actually analyze. So we're still refining that, but we do see a distinct isotopic difference between the microbial material and the stuff that's around it. We don't actually see that when we look at the geyserite. So we don't see that same fractionation of the high gallium there. It does suggest that the microbes are preferentially utilizing or silicifying with that lighter galley. In terms of the process, we've actually tried to coin a new term for a chemofabric. Because the idea is that it's not really a metabolic biosignature and that's not being used for metabolism. And it's outlining the silica that's around those microbes. But it's really difficult to tell if it's a biological process that's causing that or a non-biological process. A PhD student who's just defended her thesis proposed that what we're actually seeing is the gallium is being preferentially bonded with silica in silica oligomeric structures or monomeric silica, and that because of the structure of silica in colloidal silica, that it's not as energetically favorable to have gallium incorporated into that. So her idea is that it's actually a function of the silica polymerization. But yeah, and the idea is that in order for it to get incorporated into the EPS or into the sheath there, it has to be able to pass through very small pores. And so the colloidal silica is just too large to fit through that. So instead, the microbes preferentially absorbing those oligomers and monomers of silica with gallium. So, so what she's suggesting is that it's an abiotic silicification process, but it's a biological process that's leading to the enrichment. So there's no easy answer is the short version.
So I have a small question. So you have shown these images of this silica with porosity. So can you please comment on the origin of this porosity structure within these silica layers?
So the porosity structure is highly variable in these. The images I showed with the micro CT, really we're looking at pores that are a couple of microns up to larger pores. But there's, there's actually a nanoporosity that runs through all of this that we can't capture because of all of the silicified microorganisms. And one of the examples I was showing, it's full of diatoms. And all you're seeing in there is the exterior of the diatom skeleton with the interiors being gone. So again, that creates a nanoporosity throughout the entirety of the sample that's being superimposed then by the larger porosity. But the porosity that we're seeing recorded there is where we're seeing, again, detrital material being incorporated between those layers, or where we're starting to get larger filaments that have big gaps, but almost forming a network-like structure in between there. So that's what's generating a lot of the porosity that we're seeing.
So as you go from core to the rim, there is a evolution in the porosity structure that means in terms of its size or networking. You are getting any?
It's hard to relate it directly to size. We do see with the spicular digitate, the really fine ones, they tend to be much denser and much more evenly distributed in terms of their porosity. The bigger ones, like what Steve was showing for El Tatio, where they're larger growth structures, tend to have more obvious porosity variation, more obvious layering to them. But I can't relate necessarily the mechanism to that at this stage.
I can add a little bit to that. It's because it's a network of microbes that are living within a gooey substance. And it's the microbes that are causing the silica to precipitate. And so it's not an even homogeneous process. There's that nanoscale porosity. There's also gas that's being produced by the metabolism that gets stuck in the EPS, and those are voids that get preserved. So there's all kinds of heterogeneity, but it's actually all down to the fact that it's microbial community. And so it's an irregular material that's getting silicified.
So this porosity is generated by microorganism driven process.
There's some beautiful pictures so I can send you in Kim Handley's work.
Yeah.
That shows that really beautifully. Yeah.
Yeah.
I just have a follow-up question for probably Martin here, because have you seen these structures in Puga? Because you have worked in Puga hydrothermal plants, or have they been destroyed by geotourism? Just wanted to know.
I've heard in recent years that it's changed quite a lot, the hot spring at Puga. I think actually one of the taps has been plugged, and so there's not the same outflow. But when my student worked there, I've never been there, unfortunately, but when my student worked there, he mostly concentrated on the composition of the fluids. But yes, those deposits there, they're quite different deposits. They're not the silica deposits because they're borate rich. So they're these weird borate minerals, and they're very fluffy. They actually don't preserve particularly well in that environment, but there are microbes all through it. Absolutely. Causing extensive fractionation. To be honest, I haven't looked at that, but in those fluffy borate deposits, that's through evaporation. So that's a different type of scenario.
I had a quick question on the gallium story. It was very fascinating. But so, I mean, of course, there is perfect, correlation, the structures that you have studied and the gallium enrichments. But I've been very intrigued to understand why gallium. And first, it's a trace metal. I mean, it's possibly not very soluble in water either, right?
Yep.
And do you have any data for zinc?
Yeah, there's not much zinc.
There's no correlation because
there's no.
I mean, if you look at minerals, you have gallium and sphalerites. Right?
Gallium doesn't correlate to anything in this. First off, so gallium shows up in two different coordination environments. It shows up as a tetrahedrally coordinated ion and an octahedrally coordinated ion. Where it's octahedral, where we have more acidic conditions, lower silica fluids, then we do see it correlated to some of the other metals. But when it's in the tetrahedral coordination, which is what it is in most of these samples, it's not correlated to anything. You're right. It's very low concentration in the fluid, but it's the only element that is consistent across all the different samples that we look at. I was telling Martin just earlier, we did some great analyses just on Tuesday, where we were looking at the El Tatio sample. We did a very high resolution scan. And there we think we can see the husks from amoeba actually eating filaments. Now, the amoeba are rich in manganese. The filaments have high iron in them, but the gallium is high in both of them. So again, depending on what metal you're looking at, you're going to get a different story. But the gallium seems to be, again, the most reliable going across some of the different species.
Interesting. Yeah, because if you look at rocks in general, I mean, you either have bauxites which have some gallium enrichment, so aluminum, or sphalerites, I think the natural sources, right? But even hot springs, I mean, do you have data for the water? I mean, I don't think.
Yeah, we do. It's quite low. The highest we see in water is about 350 nanomolar.
So it's very low.
Yeah, but most of the time it's lower than that. And yet the concentration of gallium gets up, the highest we've seen is up to 1600 ppm. So, in most geologic materials, it's about 20 ppm. Even in bauxite, in the ore deposit, it's only about 100 to 150 ppm. When we look at the whole rock chemistry of these, it's comparable actually to what they're extracting for gallium in bauxite deposits.
Because, I mean, to associate, I mean, in one of your slides, you also had a bit of arsenic enrichment, right?
Yeah.
But of course, there was a big, initial story about, arsenic and life. I think Melissa Wolf's paper.
The arsenic, again, is not correlated to the gallium in these.
That's right.
Yeah.
So, I mean, I'm just curious where the gallium is because there's some oxyhydroxide. So it's purely an inorganic process that is facilitated by the environment in which these things are forming. So, or whether there is pure biological, because is it a...
Yes. So in the alkali chloride system, there's no evidence that it's associated with an oxide phase. We can see that it's tetrahedrally coordinated. It looks, from the Zane's analysis, it looks identical to a gallium enriched feldspar.
What about clay minerals? Do you have any clay minerals?
Very, very few in these. Yeah.
Interesting. That's fascinating.
And I love talking about this, so if you have other questions, feel free.
Yeah. Chat. Left one, sir. Yeah.
So we have an extended coffee break, right now. So we'll be back with the next presentation at 5 o'clock. So this is for the online audience too. I had shared, the modified schedule. So there'll be two more lectures, one by Martin and one by Vijayan, starting at 5.
Yeah, thank you.
Last one then?
No, there's one after me that actually talks about site selection process for, yeah. So that's an important one.
All right, so welcome back, all of you. I just want to do a quick check with my students who are making sure it's working on Teams. Arunava, can you hear us?
Very well.
Hi, Ramanda, I can hear you.
I can hear you.
Arunava or Kingshuk, can you hear us? All right, over to you, Martin.
Okay. Yeah. No, it's all good. All right. Well, welcome back, everybody. It's the last session for today, so we'll try and keep you interested. And I'm going to put a caveat up front here that this is going to be a very different talk from my first one. The first one was a very broad picture, origin of life. This is now down to very fine scale detail about the Columbia Hills. And it's for a very specific reason associated with why we're having this workshop, is the understanding of going to a site. What are all the different things that you can look at that site? So we've talked so far about the silica nodules with digitate structures, but there's actually a wide variety of rock types that actually span quite a range of age, we think, at this particular site. And so there's science value in addition to the silica nodules, and that's what I wanted to paint the picture of today. Sorry. So as we've already seen, there's the Spirit Rover track, the Columbia Hills, this is triangular shaped area. And you can see that it made its way down to home plate, but actually there's a very large area that was not explored by the Spirit Rover before it became stuck at home plate. And I just want to outline to you the variable different types of rocks and geology that are there. So this will be a very heavy geological talk, but I hope I can lead you through to understand how we can build up a story there and understand some of the history. So that's the area where there's of interest. And we pointed to this area of home plate, but if you look at the region around it, you'll see that there are many different types of geological textures and fabrics that are preserved. There's this feature here that almost looks the same as home plate. There's another little feature up there that looks quite similar. There's this package known as Mitchell Tree Ridge, which has already been visited by Spirit when it came down, but there's another horseshoe-shaped structure here. There's all kinds of variety just in a relatively small area. And this is worth keeping in mind that we're not asking for a rover to traverse hundreds and hundreds of kilometers. This is literally tens to hundreds of meters. This is all very doable in a mission. And I guess one of the questions, because I'm a geologist and I got trained in structural geology like some of the colleagues here today, but I've also done a lot of stratigraphy. And I wanted to do a stratigraphic analysis of what's in Columbia Hills here to get an idea of how they all sort of relate together and what part of Mars's history might they actually cover in terms of their age. So I did this a number of years ago, but I did a really detailed analysis of the geological features around the Columbia Hills. Home plate is here, but you'll see that there's a wide variety of different color terrains and a very long history of rock units that are superposed on top of each other through time. And I'll try and sort of paint that picture for you a bit today. So the oldest area, and this was visited by Spirit when it first came onto the Columbia Hills and did quite a lot of analysis in through this area, are these highland terrains. These are the topographically high areas. And when you look at them, and there's an area here which is in cross-section, You can see there's what appears to be dipping bedding, and the bedding comes towards us and fans out because of the perspective here. And that was confirmed by Spirit rover, who found a wide variety of different rock types. And you'll see that the bedding is dipping at about 30 or 20 degrees in these areas. And the different colors just represent different rock types. And with that dip of the strata, you can get a sequence of different units that are deposited. And that's what's shown here. And this is just very rough, okay? But there's a variety of different rocks, include some that have been aqueously altered. And that's all been discovered by the Spirit rover with the instrumentation that they had on board. And when we go down that area of the highlands, you'll see that there's a continuous sort of orientation in these black lines that indicates the orientation of bedding from this remotely sensed data. Now, Spirit hasn't seen any of this, but you can still see some of that dipping bedding down through there. So that seems to be a coherent package of rocks and is the oldest material in the area. Another discovery by Spirit was in this green patchy area. This is another package of rocks, olivine-bearing units that have some outcrops with carbonate alteration. It has a very distinctive thermal emissivity pattern that Steve Ruff has written about, and it was called the Algonquin class. These are high magnesium ultramafic rocks, probably tephra, which means explosive deposits, and they have this carbonate alteration. And in fact, this type of rock type is quite widespread in parts of Mars and is quite enigmatic, understanding how that carbonate alteration came to be there. It's also been the discussion as a possible astrobiological site because carbonate is known to commonly host microbes. And so there's still investigations that could be done on this unit. If we look at an oblique view, here's the highland deposits through here, and that Algonquin class sits in through here and was measured with bedding in one area, going the opposite direction to the south, whereas in these highland terrains, the dip was mostly to the north. And so you can infer that this was a small basin that was laid down on top of that older basement. And so this is a younger sequence of volcaniclastic rocks deposited on the older basement. And there's the carbonate alteration there. The third really major unit is this area in orange. It was called the inner basin because it occurs in this area, the central area of Columbia Hills, but there are patches around that look quite similar and contain quite a variety of different rocks. This is the area in orange shown in a background. This is just a topographic map, and you can see it occupies not the most high land area, but again, slightly topographically lower. So it's filling in some of the area of those eroded older hills. And there are a couple of different rock types that are preserved there that I'll go through. Right out towards the edge of the Hesperian lavas here, underneath an area that I'll talk about later, is this polygonal fractured terrain. It's quite dark in its reflectivity, and it has this very distinctive pattern. Now, that was not visited by Spirit, so we don't know what it was, but in other areas of Mars, this polygonally fractured terrain has been found to be sedimentary deposits that have undergone drying and so have fractured due to the loss of water. So it's possible these could be sedimentary deposits, but we don't know. Then there's this whole other aggregate of material in that area. The yellow is the silica deposits that we heard about from Steve. Home plate is a volcanic sequence, but there are lots of other types of materials in through here as well. And I just wanted to show you a little bit about how we built up that story of the stratigraphy. And Steve already talked about this succession that was discovered up here on the edge of home plate. And then as they went up on top of it, they found that the rocks had changed. There's this beautiful cross bedding appears, and this was interpreted as an aeolian section. So rocks that were deposited by wind action. And this lies on top of this volcanic extrusive material. And so we can again start to develop part of a stratigraphy.
We can tell which rocks are older or younger than another. We also have this incredible benefit of these very high resolution PanCam images from Spirit. And I've put this one up because you can see one rock type here. This lighter colored one is called the buff colored platy unit. The opaline silica deposits occur at the contact between then the overlying volcanic rocks through here. And what you can see is, again, the rocks are dipping into the ground. They're not perfectly flat line, but they're dipping into the ground. And that's what this symbol is representing here. So the rocks are a bit wobbly in this area, and the home plate is actually dipping inwards in all directions by about 30 degrees on the outside, but it's flat lying in the middle. It's kind of a dish-shaped structure. Whereas the bedding where this is shown comes from over in this direction here, where it's dipping off to the right. And when you look at the bedding, you can actually see changes and draw in fold axes that indicate the way the rocks have been tilted, just a little bit in this area. If we look at one exposure where the opaline silica deposits have been found, you can see here again the buff-colored platy unit, very finely bedded, probably volcaniclastic ash deposits. And then over top is a coarse lapilli tuff. This is a volcanic deposit as well. And in between, you find these nodules of the opaline silica. And you can draw contacts that are consistent with the older unit, the younger unit, and the youngest unit on top. And again, build up a stratigraphy, a history of change across this area. There are other little nodules of opaline silica that are down through here, but we think that those have been caused by gravitational deflation of the outcrop surface and those boulders or those little samples having moved. These are the consistent ones that follow the bedding and so indicate that history of geology. And so we can use this to build up more of the stratigraphy. Those were the home plate units. Here are the opaline silica deposits, and they lie on top of that buff-colored platy unit. So we're building up the stratigraphy in this area. There are other rock types that were identified by PanCam and by some geochemical analyses that are light-toned vesicular olivine basalts. And they occur in an area that is consistent with the sort of folding around the home plate. So that's older than the buff-colored, older than the opaline silica, and older than those two home plate deposits. And that smooth, deeply fractured terrain, that polygonal terrain is even lower down, so I think that's lower in the stratigraphy. And we can draw a cross-section that shows how those opaline deposits go under home plate, come out the other side, and are folded into this little buckle structure, but occur back in this other area. And we think that happens for all those different units in this interbasin area. And there's an interesting observation then up here in the north, looking out to the east. Here's the home plate strata, and it's dipping off to your right. You can see the bedding here just dipping off to the right. But if you look here, there are a number of outcrops where the bedding is perfectly flat. And in fact, that matches then this overlying vesicular basalt unit, which is also flat lying. So there's a change in the geometry of the geological units, which means that there is a hiatus in time. The older units got tilted, and then the younger units were deposited flat line on top and have not been deformed. And what's extraordinary is when you draw in the contact between the flat lying rocks and the dipping rocks, you would interpret this as what's called an unconformity, that period where the rocks have been tilted, time eroded them away, and then the next sequence was deposited on the top. And there was one photograph from just in here, which was right on that projected unconformity surface at an outcrop called Backstop. And this is what that photo looks like. There are rounded cobbles of different rock types cemented together in this coarse material through here. This is a blow up of a much wider area with that kind of texture. And this is exactly what you'd expect at an unconformity. It's a conglomerate. It looks like a bunch of different rocks have been brought in and deposited across that surface. And what that is called when you have dipping bedding and then flat line bedding on top is a sedimentary onlap with an unconformity. And that's what I've interpreted has occurred through here with a time gap in between. And so we can add on then an unconformity surface. We know that these older rocks were folded and that these ones are flat line and there was a time gap in through here. And so we're building up a picture not only of changing rocks, but changing time. And that's really important because that gives us more of interest to look at. We've heard about the changing composition of Mars through time. Well, look, we've got some volcanic rocks down here, and we've got some volcanic rocks up here across an interval of time. Now, we don't know what that range of time was, but at least we can map and see that it was there. I'm going to just focus a little bit now on this feature through here, which is just on the northern side of a feature called McCool Hill. And as we heard from Steve, that was named after one of the 7 astronauts that died in the Columbia explosion. This is a view looking up the hill, and it's not so clear from this vantage point and with the light that's on this image. But the view is looking up this structure. And you'll notice that on the hill, there's a light colored patch here, and then quite a sharp boundary with this darker material that's actually striated. And this is that contact right through here. And as you come down the hill, you see these arcuate bedding surfaces coming across the nose of that structure, and that's what's starting to form this arcuate feature here. And so this is a slope that's dipping down towards us, and it's got cover by sediment on the slope of it, heading down towards us in the valley. Importantly, right on the edge of that contact between the dark and the light material, there's a little pile of sedimentary rocks that is also flat lying that completely overlies that contact. That's again a younger succession that's lying on top of that feature. And again, we get that idea of geological time. And this is what it looks like from above. Here's that margin, the arcuate feature of the structure I'm talking about, and those Oberth deposits are deposited right across the contact. So that's a much younger geological unit. When you look at all the features, there's a number of different sort of areas within the structure, including these linear striae that you can see that are slightly fanning down the slope deposit before you get to this arcuate feature that has these wrinkly kind of concentric changes in color. This is a quite unusual feature. But when you, and then in front, it's got this quite coarse, rough texture of bouldery material out in the front, whereas this looks to be very fine grain material. And in fact, this feature, when you put it together, looks exactly like subaqueous landslide deposits. Coming down the hill slope of McCool Hill, there are these linear features that are, as the materials flows down, there are these arcuate features of the bedding in the nose of it, and there's that blocky material out at the front. So this is most likely a subaqueous landslide deposit. It's not subaerial, they look very, very different. So you can match all of the features that are in these classic submarine sequences to those, whereas a terrestrial landslide deposit is very different. It's got these fault scarps, it doesn't have the linear striae, it doesn't have the arcuate nose, and it doesn't have the blocky lobe. So they're very different, and that is a really strong inference for the presence of water at some point across the Columbia Hills. There's a second, that's the McCool Hill structure there. There's a symmetrically opposite structure on the north here that looks very similar. And so it looks like at some point there could have been water that filled Columbia, the Gusev crater before the deposition of these 3.6 Hesperian lavas. And supporting that are these little orange circles are areas where there's been evidence for hydrous alteration. And you see how they mostly occur near the contact between the old rocks and the inner basin rocks. And so could that contact represent the time when the crater was filled by a lake? The subaqueous landslide deposits support that interpretation. The polygonal fractured terrain, which is down here, support that. And there are also possible wave cut benches in the highland areas at these areas where the white arrows are. So we've been able then build up really quite an understanding of the history of events in this relatively small area. That's that last Oberth deposits here, and possibly the same in Tyrone. These represent the remnants of what looked like the youngest material in this area. Now down in the south, there's really a very different package of rocks. There's two main components. There are three little domal structures with possible flows associated with it, and then this southwest ridged terrain. And the ridges are quite distinctive here on the topographic map. And when you map them out, which I've done here in the red lines, the length of the ridges actually fan by about 25 degrees in orientation. And I'll talk about that as we move along. But the features are really quite striking. Here's one of those domes, here's another of those domes, and another one through here. And when you start to look at the different textures, there are these dark colored margins that seem to emanate out from the side of one of these domes. And similarly through here, where there are two domes, there's another dark colored unit with sort of lobate margins that seems to emanate from this point. And there's another partial dome here that looks like it's been partly excavated and is irregular. There are additional sort of flow deposits here, and those might be gravity slumps or something. And then there's a whole package of darker rocks in through here with quite distinctive texture, and then what looks like a chute coming down slope off to the west here. This lobate flow, if you look at it in more detail, has a very characteristic sort of margin, and that's quite typical of lava flows. This is one from Iceland. It looks very similar, and so the possibility is here that we have a lava flow, potentially from a volcanic source itself, these little domes. And these domes are quite unusual that they have these notched features out of the side of them. And they're also sort of dome shaped. They're not a typical volcano looking thing. You don't see a central vent. But in Iceland, there's very similar volcanoes that erupt under ice. And so they don't have a central vent. This is a flat top, but they have these notched sides because glaciers have carved down on the sides of those domes and eaten away some of the volcano. And that looks very similar to the kinds of features that we see on these little domes in Columbia Hills. So again, an intriguing, unique feature that's worth investigating to understand more about the geology and the makeup of the crust of Mars. Now that southwest ridge terrain is quite unusual. You can see that these ridges are a little bit irregular, but they generally stream away from this area where the mounds were. And in Iceland again, by using that same analog, here's Katla volcano, which is in this case covered by a glacier. Here's one of the glaciers that's cutting down the sides and etching out those notches. But when it erupts under ice, the lava builds up and it gets trapped by the ice until the heat from the eruption causes the ice to melt and it washes out in one big flood event. This is an example. This dark area is one of those big outwash catastrophic flooding events, which is a mix of basalt, eruptive products, boulders, ash, and water. It has a horrible name in Iceland. It's called a jökulhlaup. And I was fortunate enough to go there, and I wanted to just point it out. This is the texture of a jökulhlaup. It's very rough, coarse, blocky texture because the stuff comes out as a single massive event, and it breaks up these lavas and boulders. And in Columbia Hills, you've got a very similar, very rough texture in this ridge terrain. And this is what those jökulhlaups look like. There's basaltic fragments and fine glass. It's all consolidated, but often with these very big boulders. Some of them are even the size of this room, very large, catastrophic deposits. And they're also characterized by these Y-shaped structures in the ridge, in the pattern of the ridges. And we see those similar patterns at Columbia Hills. So the question is this deposit potentially a massive sub-ice lava deposit? Again, something unique to go and investigate. We can exclude the fact that those ridges in Columbia Hills are made by wind erosion. We know on Mars, as well as on Earth, that wind erosion of rocks produces these extremely linear canyons, but they don't fan in the way that they do at Columbia Hills, and they don't have those Y-shaped features. So we can exclude yardangs, as they're called, or these wind-related erosion structures as the origin of that layering on Columbia Hills. So as you see, we're starting to build up a history of events just here in the Columbia Hills. And associated with that, we have in the lower units, they've all been affected by aqueous alteration, but in the upper part of the stratigraphy, they're all been deposited under air without the influence of aqueous alteration or deposition by water. And there's really a wide variety of different types of alteration. Carbonate alteration, there's phyllosilicate and sulfate alteration. There's been a suggestion of ephemeral lakes by Steve Ruff around this Algonquin class unit. There's the development of phyllosilicates through there, and then a different type of low water rock alteration at that particular period. There's another feature that popped out when I was looking, which is this sort of peanut-shaped structure that's topographically high and texturally distinct from this ridge terrain. When you look at it in more detail, it has some interesting features. It's got this kind of star-shaped crack at the top and on the edge of these slump deposits through here. This is what it looks like on the map that we've seen before. Now, I come from Canada, and Canada is an ice country up in the north, and there are these structures called pingos that rise up from a flat surface because of ice processes. They have a very characteristic star-shaped crack in the top. That's because the surface has been raised up and it expands, so it cracks like a fresh cooked loaf of bread in the oven. And they are known to have slump deposits off the side, like shown here. And that matches to the slump deposits that are found on this structure as well. So it's possible that there's a pingo in Columbia Hills, and these structures have been found elsewhere on Mars. Up in the northern part of the inner basin, there's an area with these very irregular ovoid structures that have not been investigated and are really of uncertain origin. But following the Pingo Trail, these are not meteorite impacts because they've got embayments, they're ovoid and not circular, nor polygonal. But degraded pingos form very much the same kind of patterns. And the process is that as these form, they form these vertical structures, but as they erode, they break down and they leave behind a rim. And so the question is, here you can see this indentation. This structure looks very similar to the eroded structure up in northern Canada. So there could be older pingos that have been eroded there, again, suggesting ice processes in that region. So we have this really rich geological history in the Columbia Hills, a lot of different geological units that could be investigated. And we think that, you know, the rocks at the basement terrain are probably at least 3.8 billion years old. They're younger than the big impacts that formed the crater. But then we have evidence of a period of that warm and wet conditions with that lake fill, the hot spring deposits, potentially the pingos forming there, and then this sub-ice volcanism that goes in, which perhaps records the transition of the planet cooling down and losing its hydrous environment. And so by going to Columbia Hills, even though it's very small, you have the potential for doing a lot of really valuable science to learn about Mars's history. We were asked, and it's part of the point of this workshop, is how would you go about investigating all those questions? And I know that when the Mars mission was first announced, there was interest in a rover and potentially a drone. And the way that we see this potentially being applied is that the drone could be used for mapping and reconnaissance across this area. You heard already about a number of different outcrops with silica and areas with potential silica that haven't been visited yet. Well, with just a very light sensor and a camera on a drone, we could go and visit those sites and then decide which looks the most promising and guide the rover to those sites. So we see this as a potential new technology development possibility through this mission to do autonomous navigation guided by the drone that has a purpose in the accumulation of data, and then do the communications relay to the rover, use that to autonomously guide the rover to these different areas for sampling. It can be used for reconnaissance to look for sandy patches that need to be avoided. We heard about how Spirit came to grief because it got caught in sand here. Well, with a drone, you can avoid that and find a route that would go across those sandy areas. So whereas Ingenuity proved that you could fly a drone on Mars, it didn't have a science purpose, but now we can apply it in a meaningful and very useful way in terms of collecting data. We can talk about what kind of a tool set might be on a rover, maybe tomorrow afternoon. But one option that's already been talked about that ExoMars is doing is that in this area where the opaline silica nodules have been found, the organic molecules might be degraded in surface deposits. But knowing that these units go underneath home plate, there would be the possibility of putting a drill hole through home plate to intersect those nodules underground, where they'd be protected from that radiation and potentially contain those organic molecules that are the holy grail for astrobiology science. So this would really be about 2 meters. It's not all that thick. And we would do a more precise estimation and all the rest of it, of course. And so summarizing then, we'd have the potential for really investigating the opaline silica nodules in detail, but there's a wide variety of volcanic rocks, these sulfate soils that Steve talked about, the volcanic rocks further south, the polygonal fractured terrain. There's a whole wide variety of primary mission samples, additional astrobiology samples, material that we can investigate the hydrosphere and the atmosphere, and volcanic units to investigate Mars's mantle evolution. And so collectively, I think that's a really exciting package. So thank you again for your attention.
Land, is it because of the terrain itself, like the slope and such mission constraints wise? So would it make sense to actually land somewhere else and come here?
Yes.
Would that be a strategy?
I think like Spirit, you would land on the plains to the side and then drive to the hills and achieve your...
But the top itself is very flat. I mean, I don't remember the slopes there.
It's pretty low topography. I mean, Steve can talk to it, but the Spirit rover was able to go over the topmost of those highland terrains.
If you were to land, there is, like, it's flat enough, is it? The top of the hills itself.
You know, the original ellipse chosen for Spirit was chosen very carefully to sort of fit into a region where there was no big craters, that the rock abundance maps showed low, some low rock abundance level, slope analysis. So everything about that landing ellipse, which was huge, supported, safety of the vehicle. And certainly when we arrived, and I showed the one image, toward Columbia Hills, very smooth terrain. Rock abundance was, Matt Gollenbeck is the sort of guru of assessing rock abundance, and he's typically been right, and he was all proud how well the orbital information for rock abundance was correct based on what we found on the ground. So yeah, it's a benign terrain to the west of the Columbia Hills. the issue becomes, how long of a traverse is manageable. And so that's maybe an opportunity for better autonomous driving than what, there was minimal autonomous driving with Spirit back in the day. Perseverance has sort of come to the next level of autonomous driving. And in fact, they keep developing it. Even while it's already there, they've implemented new autonomous capability. So to me, roving Mars as autonomous driving becomes more sophisticated. It becomes maybe you just land at some place and accept that you're not going to really do science until your rover drives to the features that you really care about. So that's a scenario that I think technology will get us to that point.
Wonderful talk, Martin. I was looking at your analysis. So one thing is you are thinking of those to be slumps under marine situations?
Yeah.
You mean to say they were all covered with water?
I think from where the landslide initiates from, that could be very near the surface, but they also occur underwater. So we don't know the level of water fill.
Could it be fluidized gravity flow instead of these turbidites that you are talking about?
It's certainly possible. I'm not enough of an expert to know, but I was quite excited to compare the subaqueous versus the subaerial deposits and find that it is so extraordinarily different. And we don't really have enough information to know. Like there's not been detailed analysis of the material. So it's something to go and investigate.
Right. And the other thing is for the rover part. Yeah, is there at present any hyperspectral data on this region, over this region? No. So can a rover have a hyperspectral camera that will give us plenty of information? And another thing, not a rover, the drone. And frequently we come across, when I came across questions being asked by reviewers as to what you are seeing on surface is fine, but how much does that penetrate up to the depth? Okay, so if you are telling that what striations you are seeing actually are fold axis, and the fold is non-plunging fold, then you need to see it in sections. Often you don't get that section on Mars. So a possible answer to that could be radar data, very high resolution radar data. So any plans of having high resolution radar through drones
So this all goes to the cost benefit analysis that people have a higher pace.
These are science questions that are being posed, and these are problems where we can, think.
Yes.
Money, I don't think is a problem for any government.
No, it's about the size and the complexity. Every time you add an instrument, you increase the complexity factor. And I think one of the things that we want to discuss as a group tomorrow afternoon is really starting to, hone in on what are the key questions we're interested in, and then what are the key tools we need to answer those questions. And I'll say it to the group, and I've said it to Shyama, and we know it, that, previous missions have done all the design of the rover first, and then chosen where to go. To me, as a geologist, I throw my hands up in disbelief. True. But it's because they're largely an engineering, organization, and I think it's probably the same in Israel. And engineering is everything. You have to make it work. Yes. But I think we can save time and complexity by designing a bespoke mission architecture to solve the science questions if we identify them first. That'll make a much more efficient operation because we know what we want to achieve.
Yeah.
If you want to do everything, your rover's going to get as big as this room and it becomes too expensive and too complicated. But if you have a few very targeted questions, let's say we want to know more about volcanic Mars evolution. Okay, I need to get the best compositional data on volcanic rocks. What do I need to do that? An XRF, blah, blah, blah. I want to investigate the opaline silica deposits. What do we need to do that? I need something that grinds so I can see. I need to pick. I need to get a micro CT or whatever, we can get bespoke instrumentation that'll be able to then go into the design and then really guide the whole mission. And so it's a different approach. And I think in that way, India could be really world leading. Nobody else is doing that. We've talked to JAXA. Oh, we want to go land on Mars. Why? We want to land on Mars.
I think this time ISRO has been doing this for the Venus thing. So yes, we have thought about it, I think, in the community.
Yeah.
And yes, and joint missions are now on way, so, you know. So
Yeah,
maybe
so I
some
think that's a good,
instruments from this country, some instruments from this country, that can always be done.
that'd be
that's
so
not an
exciting.
issue right now.
Very exciting. So that's really what we want to discuss on Friday afternoon, I think. And
And
Cheyenne will lead that.
unfortunately, I have to leave today. I have a flight, I have a meeting tomorrow, so I will not be part of it, but I'll get the pre from.
Well, you've made your comment and it's well appreciated. So thank you. Yeah.
Goodbye to all. I had wonderful 2 days time today with you all today and tomorrow. Thank you once again.
Hello, sir. Mars have a water and volcano. Can we expect the pillow basalt?
That's a good question. Can you expect pillow basalts because there was water and volcanism? You might predict if there were standing bodies of water that you might find pillows. I don't know of any being recorded so far or observed on Mars. And I think they would generally be too small to observe from remote sensing. All of the studies that I've seen are these extensive lava flows that can extend for quite a long way. And in fact, I was surprised, you know, Steve said about that river channel that feeds into Gusev crater as being almost 1,000 kilometers long. And I thought, wow, can basalt flows go that long? And I looked it up. And on Earth, the longest flow is 1,600 kilometers. The longest basaltic flow is 1,600 kilometers. They can travel immense distances. So yes, if there was standing body of water and you had a volcanic eruptive event, you might expect to find pillows, but there have none that have been recorded as far as I know.
Thank you, sir.
Thanks. Yes, of course. Yeah.
I request Vijayan to upload your slides.
Yeah, so I'm just sharing my slides. Hope I'm audible.
Yeah, you're audible. Could you speak up a little bit more?
Oh, sure, I'll do that one. So
Yeah, you're audible. You're audible.
Yeah.
Yeah.
And
You can
presentation mode.
take it to full screen. Just one second. I'll turn my mic off. And in 5 seconds.
It's fine. I'm in full screen. So my full screen is visible. If someone says that I can.
Yes, it is visible. You can start.
Sure, thank you. Good evening, and thanks for the invitation. So last 2 days, a lot of Mars talk has been happening, and my talk will be about where we want to land and why we want to land, and how we get the knowledge that we have till date explored that choosing a best site. So to start with, I'll start with the Mars research at PRL. We do all sort of geological studies from fluvial, volcanic impacts, glacial, subsurface, and matroid and atmospheric, everything we do. In this talk, I'm just going to talk in specific about the surface processes was most of the things are focused, and I'll be showing examples of all the underlined one in my further talks. So what are the things we have studied till date? So all these star marks are the work done at PRL, and it includes a lot of colleagues, not myself. It includes PhD students, professors, associate professors, everyone got involved. So what these stars indicates, like we are eyeing every part of Mars. So we are good enough where we can land. That kind of confidence has gained, so that it gives idea. So all these studies says something, but we cannot land everywhere. So we have to choose. And these are not the only stars we have to choose and land. These are the ones which are already explored, So always the landing sites are welcome for new sites and explorations. So if I put in a perspective of publications, yeah, we do a lot of publications from last 2 decades. So it says that it includes atmospheric, it includes surface, subsurface, meteoroid, analogs. I'm not talking about atmosphere here because that is again a big group working in PR. And so from next slides, I'll be focusing mainly on the surface studies and how we can use those studies for the landing explorations. Yeah, nowadays people have enough Mars view, so I'm not just going it. But this dichotomy is one surprising thing on Mars. I'll be showing in the last slide why this dichotomy is somewhat important and in choosing one of the landing sites. But how it formed itself still a question whether there was an ocean or not, whether any impact ripped away the northern part of the Mars is still a question. So why it is more important, I'll be showing down the slides. One last intro slides, then I will not have because we have enough intro on Mars. This is a very good image which shows that the water earlier Mars was on the surface, but when the time becomes younger, the water get into the buried in the form of ice or permafrost kind of thing. So if you are targeting something water related or any other feature related, it is good to go to a site which is very older and be justifying which age part we have to go so that we get some good science results. This is how the early Mars looks like. I'll not. So what I'm going to do from next slide is I'll be showing some examples of studies which occurred within this latitude band and how the Mars exploration has gone through the geological timescale. So I'll be going from 4 billion years to last year on Mars, how the studies helped us to understand the Mars so that we can choose a better site for landing and exploration part. So starting with around 4 billion years, this is a volcanic dome located in the southern part of Valles Marineris. So where you can see there was a lot of impact on this volcanic dome. So what happened is it's a nearly 2 kilometers dome that got ripped off by this impact called Diana and exposed what is within a volcanic caldera or within a volcano. So it's naturally digged and exposed the surface within the volcano. And in addition to that, it has included a lot of fluvial activities and hydrated minerals. So this is a typical example of a Noachian aged volcano and fluvial processes where do you see pyroxenes and phosphorites and some sort of clay minerals indicating that this region, it's people are talking about the hydrothermal environment. This is one location where all sort of features are things like volcano, we have impacts, we have fluvial, we have primary minerals, we have glacial things. But whether this is a suitable site or not, that comes in the question when engineering constraints come. So landing on top of a dome and within a volcano is very tricky part. So that's what I'm saying in my earlier slides also. So not all the studies will be a favorable landing site, but that will fetch some ideas about what we can understand and move forward for choosing the other sites. So moving forward to the time, around the 3.5 billion years, this Perihelion crater is just located northeast of the Zero crater. So where you can see a lot of channels, fluvial channels, because there was ice deposits and that ice deposits got melted and formed these fluvial channels. And we do see SKS within that and fan deposits. So this is again a place where we have fluvial, glacial, and there are some volcanic deposits within there. So we have to choose a location where we can see all sort of geological activities and as happen. That is one thing. So again, if you look at this central peak, that is a constraint when you choose a landing ellipse. If you are putting a 30-kilometer landing ellipse, so then there are very less flat surface that are more hummocky terrain. So it may not be. So we are just choosing or understanding ourselves to choose a better site. There was a few good talks by the Gustav crater and the Spirit rover, where there was a Columbia held and the Spirit rover is there. So there was talk about what happened to the Gusu crater, whether the water came from where the Meridiana basins are and how it flowed, why there was a lack of delta fan deposits. So in one of our study, what we found, yes, this Meridiana basin, once it was filled, and that water is one of the source for this Madam valleys. And what do we found is, we found in one of this crater, we saw a very small breach in the crater rim. So that says that, and a very small fan deposits. That means this is a place where the late stage water activity has been happened. So the evidence is MG smectites. Though we do see earlier, we do find the MG smectites, which is an altered mineral that indicates there is a presence of clay and a potential site. So this is again in the follow-up of the Gusev crater where it is located, but it is within a crater, and what are the challenges that will come when we land within the crater? I'll be talking in the last slide when selecting the landing site. But it shows that it is not only the Gusev that had the fluvial deposits or the fluvial minerals. The entire Madam Valley has seen the fluvial alteration. One such evidence is seen from the Curtin MG smectite deposits. So moving forward, around 3 to 3 billion years, this is a crater just located in the eastern part of Apollinaris Mons. What do we see is a lot of fan deposits, and blue indicates the fluvial channels, indicates that this crater, though it is located in the equator, there are a lot of fluvial activities that has happened. Surprisingly, what in the floor of this crater is seen is a very good meandering channel with an alluvial fan deposits. So the meandering indicates the water was flowing and there was a avulsion was happening, and that avulsion led to change the river flow within this crater floor and lead to deposit the alluvial fan. So these coarse ridges are resistant to erosion. That's what they are able to withstand. The rest of the alluvial fan deposits got eroded by the wind because of the very old time scales that it formed. When we look at the spectra, the dark dunes, this is located just close to the Apollinaris Mons, which is a 5-kilometer tall volcano. Though it is a very good sinusoidal river, all the minerals that we could see are pyroxenes, because this Apollinaris Mons is contaminating. The ash deposits are falling over here, and if you see through chrism, you will only get the primary minerals, and the evidence of fluvial things are buried. So that is one place where we can understand that such things do happen in any other places. Though we see a primary minerals, that may be really a fluvial altered minerals present beneath that. So this is one study which proved that, yeah, these sinusoidal channels are mantled by pyroxene deposits that got emitted from these nearby volcanoes. Yeah, you can see overlapping or perpendicularly overlapping fluvial channels that indicates the water flow is from diverse directions that lead to have the superposed fan deposits. And this place is the one where we do the sinusoidal channels. So now we have channels, fan deposits, good for astrobiology, but it comes with a constraint that the region is very small and it is clumsy to land a big mission kind of thing. So this indicates that the engineering constraints plays a critical role in choosing a scientifically important or relevant science. So it has to go hand to hand, both the engineering constraints and the science, so that we can have even if it is a very small area, we can do it. But doing for the first time, it is good to go for a plain surface. So the other study is the well-known Jazira crater, the delta deposits. So within the delta deposit, there was a 2-kilometer small crater, which is called Belva. And what this delta has seen again a last stage water activity. That's what formed by this Belva crater breach. I could not able to play the video, but this is a sequence where the last stage fluvial activity happened on the Jazira delta deposits, and this water is good enough to breach this Belva rim and continued outside. So what happens is, though we are targeting on delta deposits or the alluvial deposits, there is always a last stage fluvial activity happening. So if we go there, we can see how these water activities spanned over the time from early Noachian to earliest period. So one interesting site, this is around 5-meter boulder, and this boulder is got transported by this wind, by this water, and the last stage water activity, that's what it is hanging over near this bell valve. It is exactly from here, and this is from the Perseverance. So moving forward to 3 billion years, yeah, more water. But where these waters are found is an interesting part. This is one of the graben-oriented water deposits. We do see it on tops of the largest lines. So it is just located on the east of Olympus Mons, and we do a lot of fluvial channels with very good streamline islands forming over it. So this is a place where we can see this is definitely a groundwater release punctured graben. So that's what there was, a catastrophic release of water, and it had formed. But you can see post these water activities, you can see the lava flows emanating, and they are filling these fluvial evidence. So whether this would be a good site, we have lava, we have fluvial deposits, we have graben tectonic activities. But the constraints comes is this region is highly dusty. So if a mission is planned with solar panel, and the rover is going to work on solar panel, and this is not an advisable area because the dust deposits within days is going to be huge. That is going to affect the sunlight that is going coming on the solar panel. So we study all these things. We are not wholehearted, or we are not attached to the locations where we are preferring. So that means these studies give more ideas. So the best evidence for the thing is the streamline island, which is an evidence of fluvial activity presence on a volcanic terrain. Yeah, so moving forward to around 1 billion years, yeah, there are impacts and there are tectonic activities happening on the close of the Valles Marineris, whether that could be one potential target sites where we can look for a large-scale tectonic activities. Yeah, this could be a region where we can explore. So because this Ketina, elongated pits due to a subsurface collapse happening within the adjoining region of the Valles Marineris, so you can see that is a cross-cutting within this Pittal crater, and you can see the Ketina is at least 1 kilometer deep than the crater itself. So that means if your mission is planned with a seismometer or a seismic thing, so this is one of the sites that is for to understand about the internal activities, whereas we have already an InSight mission near the Cerberus Foci region. You can see this. This is an evidence where these Valles Marineris is slowly growing over time, and it is not one-time event. So that means the tectonic activities are occurring till date or very recent past, so that we can say it's over time. It is these big chains are elongated in the direction east-west. Yeah, if you go to higher latitudes, we look for glacial or very shallow surface ice. So this is one studies where we have seen the fan deposits within the crater, and they got inverted. But as I mentioned, so it's a very, very small area to land. So it's very tricky to land within this short period. So the other studies, if a GPR or a radar is planned within the things, there are a lot of LDA deposits, and some of my colleagues very thoroughly study about these things. They will look into the morphology, and they look into the radar from Sharad, what is the possibility extent of these ice deposits. Yeah, I do understand it is impossible to land on a slope surface because the LDA is having a steep slope. One best possible region is landing nearby, but still we get the subsurface ice deposits. Again, this is happening around 35° north. So again, the conditions comes into pictures whether we can land in the higher latitudes, whether any CO2 frost deposits will have an effect. They're coming to very recent time, like 0.5 billion years kind of thing. So what we do see is like when we see about the in situ, whether what is the ice present and how we can utilize that ice, or how much ice is present. So one of our studies show that yes, at 50 higher latitudes there are a lot of ice, exposed ice, and they are very well matches with the Chrism observed a spectra with a laboratory running spectra, saying that for future in situ resource utilizations, the ice deposits are plenty on Mars, and it is in the very shallow subsurface. Again, the locations, we understand the location is on the steep crater wall, which is currently difficult to land it, but it gives an idea that at this region, even in the outer region, we can see a lot of ice deposits buried that is useful for the potential ISRU in future. So this study showed that there are diverse places these ice deposits are there, and if we connect these two dots, probably there are more such locations within this. So if a mission is more interested towards the subsurface ice, exploring the extent of ice, so these are the locations favorable. But it comes with the constraints whether we can go beyond 35° in both the hemispheres with a solar-powered rover without affecting the CO2 frost deposits. Yeah, this is just an example to show those things. Yeah, when we say analogs, we will not say the analogs only for the geomorphological conditions, but we do say for what is the climatic environment that prevailed on Earth and on the Mars. So what I want to say from this picture is like, why some of the missions focus more on the fan deposits or in the bottom of the fan deposits? Because the ice melts and forms this fan along with the water. But when this fan sometimes hosts very extended stage of lakes, small to large scale deposits. So same conditions may have prevailed on this part. You can see a small extension coming out of this fan deposit, saying that there may be a probability of more short to long-term lake deposits over this part. That is, which if you talk about the astrobiology, so one of the target region is going to this kind of place instead of climb such a steep fan deposits. So it's not only astrobiology, it includes all sort of things, whether if you have like Zazero, where there was a delta in one such locations is more favorable to for emissions if you are going one time or first starting. Coming much younger, so there was a report that the Keel crater has released some methane, and whether it is abiotic or biotic, and what is the reason for such things came a few years ago, and it's a debate. So it's one such crater. It's still in the higher latitudes where we can see a wrinkles cross-cutting the crater CCF. So where you can say because of this wrinkle activities, we can see a small scale ruptures. These structures will give small scale tectonics, and they do release the volatiles. So this are the sites where the missions are more interested towards understanding about the seismic and the volatiles release. So such combo of locations are preferable for that kind of missions. And coming to the last few years activity, these are the boulder falls. They are nothing but when a rock falls from top to bottom, they form these kind of herringbone patterns. I'm saying that they are occurring in large numbers on Mars. So these rocks are few tons in size. So what is the phenomenon that triggers these ton-sized rocks, 10 kilograms rocks from a steep slope? That is a quest. So in one of our studies, we used the highness data and found that where the InSight mission has landed, so that is have detected a lot of seismic activities along the graben, and this graben walls are witnessing the recent day boulder falls. So it is very well the InSight mission has been chosen, the landing site has been chosen because they want to do the seismic study. One of how they chosen one of the ways they found a lot of grebens with a lot of boulders which has fallen from the cliff. So that means these ton-sized boulders cannot be moved from wind or just by the slope or just by the diurnal variation that is occurring on the Mars. It needed a good amount of momentum for these rocks to fall down the slopes. And when InSight went, it measured a lot of quakes, and the biggest is S122A with a magnitude of greater than 4. which justifies that the landing site chosen is one of the potential site to study the seismic event. So it is how we have to choose it from these studies help to choose the better sites rather than focusing on one or two sites kind of thing. So last but few slides, yes, we know we are going with some sort of solar power panel. So how does this dusty region is going to help? Because this dusty region is going to definitely play a role in affecting the solar insulation of the panels, and that is going to reduce the efficiency of the rover. So that means these are the regions to be not discarded, or it has to be taken with a note whether we want to challenge our mission to go on such sites. That is one school of thought we have to put. If you put it that one, last but one slide. So if you put it this, all these missions are mostly targeted towards the dichotomies because they are seeing a lot of evidence of all these geomorphological evidence of fluvial, glacial, volcanic things are present. If you put it over in a perspective, it is one site place where it is, we see all activities in one condition. So in summary, if I want to say where we want to go, what is the preferred geological time period for the landing site is, it is the first 1 billion year. The reason is the first 1 billion year of Mars witnessed all the activities that what we are seeing currently on Earth, from fluvial, volcanic, very well preserved atmosphere. Everything was there within the first 1 billion years, or within less than the first 1 billion years. So choosing a site within the first 1 billion year with all sort of geological activities will be the most favorable site for the first Indian missions to explore the new Martian signs. So this is a box which I was showing, saying that these are the preferred regions we can go. And within this, there are multiple people, multiple studies has occurred. So that discussion has to happen in down the time with very seriously to choose one of the sites from this, so that we can cover the geology, the climate, the astrobiology, and in situ all in one nutshell, so that we can do it. But coming to the safety, yes, if you look at the most of the global missions, the first missions, they mostly prefer the safety has a higher priority because they are not choosing any deep valleys, very deep craters, or not dusty regions or hummocky terrains, because the first thing is to land safely. There are many places which are flat, which are very good in scientific exposure. So in that thing, I end my talk. I'm happy to take any questions if it is. Thank you.
Thanks, Vijayan. Just check if there are any questions here. Comments? Yeah, Martin.
Hi, Vijayan. It's Martin here. Nice talk. Thank you for such an amazing overview of a big body of work by your organization. I'm interested what you think is a really penetrating science question around fluvial processes. Several missions have already investigated. Perseverance rover has driven up a delta and into a fluvial channel. What is it specifically that you think going to a fluvial area will add to the knowledge about the science of Mars?
Okay, so I would prefer, I don't want to go to a place where only fluvial activities occurred. So I'll prefer a site where there is, along with the fluvial, there is other geological activities also happening. Because it's a one-time mission we are going, so going for one specific geological activities should not be the targets. To answer your question, what new things we can form? So always I'll take the examples from the moon. So moon, people say the evidence of water it is. But when Chandrayaan-1 went, it is gave more consolidated evidence that there is a wide presence of water. So that opened up a new research area in exploring the volatiles or water-related activities of the moon. So in the similar perspective, if you move it towards Mars, there are very very diverse regions which has fluvial deposits along with other geological properties. So, so we have to choose what we learned from this is we could not see any small single shells or any microbial things. That means Mars is telling us that we have fluvial things, but I buried it below the dust of Mars. So the mission should go somewhere with exploring the subsurface things around the fluvial and other activities to explore any possible microbial signatures.
Yep. Thank you. And okay, I guess it's already pretty late, and thank you for staying up this late to present. So I think with this, we'll possibly end today's session. Thanks to all the online participants, as well as, of course, everyone who's present here in person. So we will meet again tomorrow morning, starting at 9 o'clock. So thank you again. See you tomorrow.